your sessions. Those who have their presentation in 3A are requested to remain here. Those who want to join 3B, 3C, they can move to those sessions through breakout rooms. Okay, so we are going to start our session 3A. Welcome to session 3A. And I take this opportunity to introduce our session chair, Professor S.P. Pandey. Dr. S.P. Pandey obtained his PhD in the year 2001 from Banaras Hindu University, Varanasi. During his PhD, his research topic was swift ion irradiation effects on electronic devices, such as metal semiconductor devices and silicon solar cells. Dr. Pandey has visited National Taiwan University, Taiwan as postdoctoral fellow. There he got expertise in the area of crystalline and polycrystalline silicon solar cell. Dr. Pandey has vast teaching experience of 20 years at the UG and PG level as science and engineering both. His research expertise is on semiconductor devices, crystalline solar cells, and third generation solar cells. He has also worked as visiting professor at Kano University of Science and Technology, Nigeria. He has published several research papers of national and international repute. Dr. Pandey has completed 3 DST-sponsored projects on the development of solar cells and related materials. He participated and presented papers in several national and international conferences and is a potential reviewer of national and international journals. Currently, he is working as a professor in the Department of Physics at Tirthankar Mahavir University, Moradabad, UP in India. So let's welcome Professor Pandey to chair this session. Professor Pandey, please.
Thank you, Dr. Ganesh. Very good morning to all of you. Today's session, it is third day of National of Material. So, in today's session, there are 8 speakers, and 8 speakers, 7 are related talk, and 1 is plenary talk. So, invited talk, 1 speaker from New Zealand, 1 speaker from India, and 1 plenary talk, it will be from. On behalf of chair of this session, I would like to welcome all speakers as well as participants in function. So we start our session. First invited speaker, Professor Neelam Srivastava. Her topic of presentation is starch-based polymer in salt, a new hope for all solid-state flexible energy devices. Now, ma'am, you have only 30 minutes query. Now, over to you to start your presentation. Hello. Neelam, ma'am?
She is online.
I was muted actually. That's why I was not able to do it. No? Okay, now I am presenting my paper.
Yes, yes.
Okay.
Okay, thank you. Thank you.
I think my screen is now visible to all of you. Na? Okay, thank you very much. Thank you very much for kind words and thank you to the Professor Pramod Singh and the organizing committee for giving me this opportunity for delivering my talk, which is related with the polymer in salt electrolyte membranes, a new hope for the all solid state flexible devices. Just to start from the very basic fundamental things that what we are nowadays seeing is that your electronic technology is marching ahead with a great pace, and we are daily we are getting a new devices which are becoming a part and parcel of our daily life. And these are they have reached up to the this health monitoring systems, and they have become an part and parcel of our exactly daily life. We cannot think about living without these devices. And as the electronic devices are marching ahead with the mm, with a great pace, so they require the energy devices of the same level. And so these energy devices which are required in these special electronic devices requires a small volume, lightweight, and good electrochemical properties. Besides this, when these electronic devices come to the level of wearable electronics, which we are using nowadays are in a great number, then the safety measures becomes a very important parameter. And just a minute, yes. And then safety becomes a very important parameters, and the mechanical durability in terms of stretching or twisting reliability becomes a very important part. And the high energy density is also required for in all these devices. So if we look into the system of these energy devices, the basic component of all these energy devices are electrodes and electrolytes. And when these devices come to the flexible region, then both these electrode and electrolytes need to be the flexible enough to for number of cycles, so that they can accommodate the flexibility of the electronic devices. So a lot of work is being carried out in both the field, in the field of electrodes and electrolytes, and tremendous success have been achieved in the field of flexible electrodes. But as far as the flexible electrolytes are concerned, we are still dependent upon the systems having the liquid component in it, because all solid state devices are either very rigid, or they have a very poor uh, electrochemical performance. So at this present state, all the commercial electronic devices are using lithium polymer electrolyte, because these electrolytes are because these electrolytes have the properties of the electrochemical properties approaching to the liquid systems, and they have the benefit of the solid physics, of having the solid physics. But still, although they have achieved a great success, but still their conductivity is restricted because of the solid physics, and a small amount of the liquid component needs to be added in the system to get a better conductivity in these devices. And especially when it comes to the flexible devices, it is not possible with these polymer electrolytes that they are flexible enough and are giving the good electrochemical properties both. So why this problem is associated with the polymer electrolyte is that this in polymer electrolytes, the segmental motion, the ion transport comes through the segmental motion. And in the segmental motion, this is a very typical picture of the segmental motion, where you can see that if we consider this as these sketches as the polymer backbone, then you can see that the side chains are moving and transferring the ions from one place to the other. And the same is shown in the lower figure also, and that how they move the movement of the segmental branches. This green color ion, if the green color represents the ion, how the ion moves from the one branch to the other branch. Because the segments of the polymer are quite heavy, and hence their movement is quite slow, so ultimately it slows down the uh, conductivity of the ion. So it is a great problem in these polymer electrolyte, sorry, which has to be checked out, or which has to be improved. In 1990s, a new concept has been given, that that if we put large amount of the salt in these polymers, then there will be a condition when the salt dissociated ions make a cluster throughout the matrix of the system, and then the ion will transport through these ion clusters. And because there will be no segmental motion associated with these transport, so the ion transport will be high and very good. And this concept has led to the classification of polymer electrolytes into the two categories. One is salt in polymer electrolyte, and the other one is the polymer in salt electrolyte, which you can understand from this figure, that if we start with the polymer and we start putting the salt till this near PISC system, where the throughout the main, there is no clustering throughout, the threshold is not achieved, cluster threshold is not achieved, till then the ion transport will be through polymer segmental motion. And once the threshold has been achieved, the ion transport will be through ion matrix. So it divides in the whole polymer electrolyte into the two parts, where the salt concentration is low, and the other one is where the salt concentration is high. And what is required for the salt concentration, what is required for the this PISC system? So the polymer host should be good enough to accommodate a very large amount of the salt and keep it in the dissociated form. It is not only accommodating the salt, but to keep it in the dissociated form. At the same time, it can hold a large amount of the salt and keep the matrix flexible enough. The problems which has been recognized till now, if you go through the literature, you will find that whenever you try in a PISC system, either you end up with the poor mechanical properties because too much salt are making the matrix little bit brittle, or the salt association is taking place. So ultimately your uh, electrochemical properties are not good enough. So our group has decided, because it is very promising system PISC, because the ion motion through the cluster means a very fast ion transport. So we have decided to work in this field and to to target both electrochemical as well as mechanical properties to be achieved at the same time. If you consider that when we are doing research, then it is not, if you are limited to the laboratory work, it's okay. If we are just trying to do some work and doing some analysis, but if you are targeting that, if you can reach to the commercial level, then the additional properties are required, because a material
Professor
can reach to the
Srivastava.
commercial. Hello?
Excuse me, Professor. Can you please keep your microphone close to your mouth?
Okay. Sure.
Sorry for interrupting.
No. Okay. So when you try to reach the commercial level, then along with the electrochemical properties, you need some additional properties, because until unless your system is economical, it cannot be commercially entertained by the companies, and they should be easy to handle, so that when you try to make it in different shape and size, they should be easily accommodated, so that you can cut into different shape and size, you can pour it, or different things, facility should be there. And of course, when it comes to the wearable electronics, the safety becomes the major concern, as I have already told you. So these are the important points when you choose a polymer host for the PISC system. So our group has selected the starch as an host polymer for such system, because starch being the renewable polymer, they are environment benign, they are cost effective. We know they are very cheap material, very easily available in the market, and at the same time they possess the basic properties of the host polymer, that they accept salt, they can be developed in the membrane form. And on the most important property of the starch, which is very fascinating, is that when you add the salt to these systems, they break the starch. The starch molecule is broken into the smaller molecular weight molecules, and which makes the flexibility, increases the flexibility of the system, and also it provides more number of moieties to be interacted with for the interaction with the salt. And because of this, what happens that more amount of the salt can be added, and it can remain in the dissociated form, because moieties are available to interact with this salt. When we tried to first tried this type of system, we encountered such a great failure that because all the system was, the moment we left the system to dry, this end up with the fungal growth on the system, which not only decreasing its mechanical property, but it was affecting the electrochemical properties also. So we have tried different methods using some preservatives, using alternative low cost solvents available, optimizing the preparatory conditions, exploring different starch, and cross linking the starch with the appropriate cross linkers. So in all these methods, we found that the cross linking with the starch with the appropriate cross linker is a sorry, it's a very simple and important method. And for this, if you see this, this is the starch matrix, and these HOMOATs are used uh, for the interaction with the salt. But when you put GA in the system, the glutaraldehyde we have used in the system as an cross linker, this GA interacts with these moieties. So it has been observed that the amount of the GA is going to affect the conductivity of the system. So it has limited us to use a compromised value of the GA to achieve the good highly conducting system. So we found that if we put in 1 gram of salt, if we put 2 ml of GA, then the system is quite good and good. We can easily develop freestanding, nicely transparent film. And the system preparation method is very simple, doesn't need any technologically, no advanced instrument, nothing is required. Simple, take beakers, use salt solvent, use starch solution, make salt solution, and stir them at a proper temperature. This temperature changes with the different salt. This is for the potato. Like this wheat, if you go for the wheat, it requires 70 degrees. So it depends upon the temperature, depend upon the starch. So you have to use this, vary this, and put some amount of the GA in the system, let it to dry, and you will end up with the nice freestanding film. So a very nice protocol has been developed by us, and we have found that if we vary the salt concentration from the this concentration which is mentioned here, means what we are using in the 1 gram of salt, and how much 1 gram of starch and how much gram of the salt. So till the starch is 1 and salt amount is less than 0.6, till then we are in SIPE system, that means salt in polymer electrolyte system. But the moment we have increased the amount of salt more greater than 0.6, then it has transferred into the PISC system. And both the groups have their own importance, but in today's talk I am limiting myself to the PISC system. This is the total salt concentration variation. You can see that after 0.6, 0.7 gram of salt, the conductivity has reached to a very high value. This is the conductivity, and this is the moisture content. And of course, the moisture content has also increased, but please remember this moisture content is binded in a bound condition, so it doesn't come out as it is in a very easy form. So that is a very good thing with the system. So we have this is different systems for which we have studied using our protocol, and we are happy to inform that we have got success in developing so many transparent freestanding films which can be bent into the different shape and size. You can twist them, you can stretch them. So excellent. This is potato starch, and like this, when we tried wheat starch, we got success. NaClO4 with also we got success. With this is the wheat starch which I have shown there. You can stretch them, twist them, bend them. You can do any kind of flexibility test with these materials. Arrowroot starch has also shown the similar kind of behavior. This is corn starch. We have changed the salt also. There it was sodium. Here we are using magnesium. We are getting the same level of success with these salt also. Even with the magnesium salt, sorry, I have cold problem, so extremely sorry. So with the magnesium salt also, the transparency increases little bit. So these systems are very excellent systems for the from this mechanical point of view. So all these systems which we have studied, and which we see for the application point of view, we need high ionic conductivity, we need wide electrochemical stability, we need low ESR matlab equivalent series resistance, we need low relaxation time, and we need EDLC type of charging discharging behavior for the, because my concentration is more on the super capacitor. So EDLC type of charging behavior is required for my system. And mechanical but natural, that you need flexibility, stretchability, non-toxic, non-volatile nature, good physics, long durability, low salt. All these have been achieved, and for this we will see in the coming data. So we have published many papers that you can see the resistance is very small, less than 1. And you can, one thing I want to inform here, that this resistance is for 0.8 thickness film, and the film thickness can be reduced by many fold using simple techniques. And so that means it indicates that you can have a very large, very small resistance with these materials. This is electrochemical stability window, quite long, quite wide, that's very good. The electrochemical stability window changes with the salt concentration. As you increase the salt concentration, it little bit slightly decrease, you can observe, but it's okay. There is a compromise between the conductivity and electrochemical stability window as you increase the salt concentration. So it is up to you that what range you want to have for your device. So you can play with the salt concentration and get same kind of device for these things. You can get same kind of parameters for you according to your device application. This is the fast and transport method. You can check, you can see, which we have measured from, we have measured that ion relaxation time using the imaginary capacitance, plotting the imaginary capacitance with respect to the frequency, and we found that all these are in the range of microsecond. And as the salt concentration is increasing, this charge, this ion relaxation time is also decreasing, because the better the ion cluster throughout the matrix, the easier will be ion, transport. So faster ion transport is being observed. So this is also a very good. Here I have summarized some of the values, that how it increases. This is for wheat starch, and this is for corn starch. This is with NAI system. This is for magnesium. And you can see that wide ESW, low this resistance, as you increase the salt concentration, ESR is low. But better ESR is you observe when this is NAI, which is very obvious, because sodium is much lighter than the magnesium. So it will be, must be having a slight means slower transport in comparison to the sodium. So the same can be observed from the tau value also. For the magnesium, we have a little bit higher tau value, whereas for sodium, we are having lower. The conductivity is also of the very high, 10 to the minus 2. And it, for magnesium, it is of the order of 10 to the minus 3. And if we increase the salt concentration, the students have studied till 1:1. We are trying to study for a higher value of salt concentration, and hope that it will increase further. And when we try to understand its cyclic voltammetry, and we are so happy to see that they are forming exact parallel nature. So exact rectangular nature, though it has, and this has been observed for a very high value. That means the charge transport is very high, and they are able to have depict such kind of behavior at a very high scan rate also. The similar kind of studies has been observed for the other system, potato, and this is for different corn star system. I'm just showing different data. This is for arrowroot star system, and for magnesium salt. You can find that everywhere the desired properties are very well maintained. Of course, some difference in the scan rate is observed. That is very obvious, which will different from the depending upon the salt and the salt movement. It, of course, it has to be different. So there is a difference, but quite a good behavior has been observed for the all the systems. And recently, since the system electrolyte material was showing very good properties, so we tried to test our system with the well-known available electrode materials, which are very common, and on which large amount of many number of studies have already been carried out. These two were the anodized aluminum and Teflon coated carbon cloth, which are available commercially. So we started our studies with this, and this study we found we have used this kind of structure stacking system for the measurement of for the fabrication of the systems cell. So this is how we have used it. So you can see that here also we have got good low resistance. Again, I am repeating that it is for 0.8 mm, and hence please remember, when we will target it for commercial application, we can use the thickness to a great level, and hence the ESR value will go certainly go very less. So it is a very good result from our understanding, that it is really a very exciting result for us. And they have shown the similar kind of behavior as far as your LSV is concerned, the similar which has been observed with the other electrolyte systems. So it is again a very encouraging result for us. The rectangular behavior has been maintained by these two set of cell morphology, cell fabrication structure, and the cycling is also very good. We have observed good cyclic behavior. So at the end, if we try to summarize our value and try to compare with the available other system, electrolyte system, where as we so we can see that we can compare it with the ionic liquid, hydrogel electrolyte, liquid electrolyte, and other solid polymer electrolyte. Ionic liquid, of course, the ionic liquid shows the best ESW. Electrochemical stability window is very wide, 3 to 4. But one should remember that ionic liquids are very costly systems. So when it comes to the commercial application, it is always a question under question that how to use it. And our system have shown 2.5 to 4.5, where ours with the and also with the cost effectiveness of the system. So this is really very encouraging result which we have observed. ESR value, and with the ionic liquid it has been reported like this, 3.3 to 8, and for other system it is even higher. For our system it is less than 5 ohms. So again, good result. With the ionic system, ionic liquids, we have observed is gel electrolyte. This all like our system is flexible. It can be twist, you can bend, stretch everything. So it is good again. That relaxation time in seconds, where we are getting in microseconds, again a good thing. Conductivity also very good if you compare with the all. And resonance frequency is very high. That is a very important thing, because resonance frequency puts an upper limit to your system. So if we summarize our result, we can say that the salt modified star systems can be synthesized at a very high salt concentration. You can reach even higher than 1:5 star salt ratio. We studied till 3 because of mechanical controlling mechanical problems. They are very flexible and we don't have systems to handle that. Otherwise you can measure them also. They are flexible, they can be molded into different shape and size, have high conductivity, low ESR, very fast ion conduction, good transparency, electrical properties varies along with the salt concentration, so you can mold them according to your requirement. It has advantage in comparison to many existing electrolyte. The cost effectiveness is this: 1 centimeter to 1 centimeter system will cost you only rupees 25. So we think that and besides having all these important electrochemical parameters, they are economical, easy to prepare, and electronic environment friendly. So we found it, the system is very good, and now we are looking for some company to collaborate so that they can be tested for commercial level, and we can overcome all the problems if there are any. Thank you very much.
Okay, ma'am. Okay. Thank you for your nice and informative presentation. And now this presentation is open for discussion. If you have any query from the participants, I have one query, ma'am, from Kamlesh F02. Yes. According to him, what is the lifespan and temperature window of these membranes? And what is the meaning? What is the meaning of low cost solvent? Even it was my question also. Please.
Low cost solvent. Okay. Means that we are using simple acetone, methanol, which are easily available, and we started with the water, but water is not good because you will get the end up with the fungus in those system. So we dropped the water. We had to drop the water. But if you use methanol and acetone, they are excellent solvent, and then you can go with them. They are easily available, and they are, it's quite cheap in comparison to the other. And as far as life is concerned, my students are using it for means at least they, throughout their PhD period, they maintain it 4-5 years. We have not observed any reportable degradation in the system. So
generally, biopolymers getting affected with fungal problem after certain time. So that's why this question may be asked.
No, that's why I am saying we encountered this problem at the very first stage. We got the fungus. So after cross-linking, there is no fungus. The film remains as it is, nice, flexible, excellent material. It maintains itself. It's really very good.
Okay, thank you, ma'am. Any other query from participants? I think so. Thank you, ma'am, again.
There is another question. If ma'am is still here.
Yes.
What about the? This is from Natalie Carolina. Her question is: what about the contamination with other cations as protons?
No, protons as it is, we have not tried. We are working on the sodium and magnesium systems. We have not tried with the acid. Acids generally, actually we tried with the acid. Acid is not successful, to be very honest. And we work with the sodium and magnesium. These salts are successful. And no cation at all. No cation at all. No contamination at all. No contamination. We didn't observe any kind of problem with the system once we have added the glutaraldehyde. After adding the glutaraldehyde, it's really very system is very stable and free from any kind of problem. Their question is there: how you dissolve biopolymer in alcohols. Okay, we can see that actually you cannot dissolve as such. Dissolution means that, but it makes a homogeneous type of solution. It means what to say, that it absorbs the methanol and it swallow something solvent type of behavior is observed, which is good enough to mix the salt in it. After that it makes the okay. Next question is at which level we should add glutaraldehyde. Of course, once
which level we should
after adding up the salt and in starch just after stirring for 2 to 5 minutes. There is no such guidelines, but generally 2 to 5 minutes we add the glutaraldehydes. There is no such a well-defined time limit that when to add it. You can add even simultaneously. There is no problem.
Okay, thank you so much, ma'am. Sir,
Any other query? Okay. Okay, ma'am.
Okay, thank you.
Say something.
please continue with the next. We'll continue with the next presentation.
Okay. Okay. Thank you, ma'am, for your informative presentation. Now, next speaker is from New Zealand, Professor Marilo Kadadal Raduba. Professor Raduba, her topic of presentation is rare earth doped fluoride glass as fast response scintillator for neutron detector in nuclear fusion reaction. So, Professor Raduba, okay, Professor Raduba.
Yeah,
Okay.
hello, good morning,
Okay.
everyone.
Over
Can
to
you hear me? And can you see my screen that I'm sharing?
Yes, it is visible.
Yeah, it's all good. Very good. Yeah. All right. Yeah, so good morning to everyone in India. It's afternoon in New Zealand. Thank you very much, Professor Pandi, for the introduction. I would also like to thank Professor Singh and the organizers of this conference for inviting me to give a talk at this 4th International Conference on Science and Engineering of Materials. On behalf of my colleagues at Osaka University in Japan and my collaborators at Tohoku University in Japan, University of Wrocław in Poland, and University of Lyon in France, it's my honor to present our work on the rare earth doped fluoride glass as fast response scintillators for neutron detection in nuclear fusion experiments. As Professor Pandyas introduced, my name is Mary Lou, and I work at Massey University in New Zealand, but I also am working at Osaka University in Japan. Right. So first, let me discuss what is a scintillator. Essentially, a scintillator is any material that is used to detect ionizing radiation via the emission of photons. So you have this material that absorbs the ionizing radiation. Electrons and holes are created. When electrons and holes recombine, they emit light, and it's this emitted light or luminescence that we call scintillation light that is detected by conventional photon detectors like charge coupled devices or photomultiplier tubes. And these signals are converted to electrical signals, which allows us to interpret the original radiation that stroke the scintillator. So the scintillation works through this mechanism shown in this slide. You have the material that absorbs ionizing radiation or high energy particles, and that creates a hole in the core levels and electrons in the conduction band. When the energies of the electrons become less than the ionization threshold, the electrons and holes thermalize to the bottom of the conduction band and the top of the valence band, respectively. The electrons and holes then migrate to the luminescent centers or the activator ion centers. And when the electrons recombine with the holes, photons are emitted. It's these photons that we see as luminescence and we detect as scintillation light. So this picture shows a plastic scintillator that is used to measure beam backgrounds at the photon factory in Japan. When this scintillator absorbs high energy radiation, in this case, this is a vacuum ultraviolet lamp, the scintillator fluoresces, and the blue light that you see coming out of this excited scintillator is the luminescence emission that we detect as scintillation light. So scintillators have many applications in medicine, security, astronomy, imaging, and scientific research. Essentially, any application that requires ionizing radiation will have some sort of scintillator in it to detect the ionizing radiation. And in fact, there is a huge demand for scintillators, so that the global scintillator market is a multi-million-dollar industry that is projected to cost over $400 million by the year 2025. So there is a lot of research going into materials for scintillators, and there is already a large number of existing scintillators. This graph shows just some examples of the scintillators that have been developed, but still there is continued search for scintillators due to the requirements imposed by various applications, which a single scintillator cannot satisfy. This figure here on the right shows two characteristics that are important in the scintillator development. Of course, luminescence intensity. The scintillator should have enough light output in order for detection to be possible. But at the same time, fluorescence decay time or luminescence decay time, or the response time of the scintillator, is also important. We can see here that there's a trade-off between intensity and decay time. So if we want a very intense, bright scintillator, we'll usually have to sacrifice response time, and you have here a slower response time. If you want a very fast scintillator, then you'll have to deal with very low light intensity. So in some applications, you want a fast scintillator. For example, if you're using time of flight. In other applications, a slow scintillator is enough. If, for example, you're using it for dosimetry, for example. For our particular work, for our application, we're interested in developing scintillators for detecting neutrons in laser fusion. So this is the laser fusion GECO 12 facility in Osaka University. It consists of 12 beam lines. So each of these green pipes correspond to a laser beam line. There are 12 beam lines from an ND glass laser. And we focus these 12 beam lines into a 50 micrometer radius spot. And in this very small radius and very high energy laser beam, we generate fusion plasma. As shown in this bright spot here is the fusion plasma that's generated. In the fusion plasma, we can see that there are primary neutrons, which are very intense and high energy, 2.45 mega electron volts of energy. At the same time, we also have scattered neutrons, which are at a lower energy. The ratio between the scattered and the primary neutrons is proportional to the density of the fusion plasma that's generated. So it's thought that if we wanted to control laser fusion, we should be able to control the density of the fusion plasma. And therefore, it's very important to be able to measure the ratio of these scattered neutrons and primary neutrons in the fusion plasma that's generated. But that's not so easy. If we can see here, this shows the energy spectrum of the neutrons. We can see these primary neutrons at around 2.5 mega electron volts. It's high energy, but it's also intense. So it's quite easy to detect the primary neutrons. But if we look at this lower energy region, we can see these scattered neutrons that are weaker than the primary neutrons. And it's these scattered neutrons, the detection of these scattered neutrons is quite problematic because they are easily swamped out by these intense primary neutrons. But if we look at this black curve here, it's the interaction cross-section of lithium-6 with the neutrons. We can see that lithium-6 has a high cross-section of interaction with the scattered neutrons. So So if we wanted to detect the scattered neutrons, we should use a scintillator with a high lithium-6 content. Essentially, the neutrons will interact with the lithium-6, and that interaction will generate triton and alpha rays. The alpha rays will then excite the scintillator, and the scintillator will emit luminescence, and which this luminescence is what we can detect and relate back to the scattered neutrons that interacted with lithium-6. So that's the first consideration for developing the scintillator. There should be a high lithium-6 content, but we should also take into account the response time of the scintillator. So we measure the scattered neutrons using the time of flight measurement technique. Essentially, if this is your fusion plasma, we place the detector at a fixed distance from the plasma chamber. In this case, for example, 30 centimeters away from the plasma chamber. In the fusion plasma, X-rays are generated as well as primary neutrons and scattered neutrons. And these three have different speeds. So they travel at different speeds. X-ray is the fastest, while scattered neutrons are the slowest. So by having a fixed distance and different speeds, that means that these X-rays, primary and scattered neutrons, arrive at the detector at different times. X-rays are the fastest, so they arrive first, followed by the primary neutrons, and then the scattered neutrons. So if we calculate the time difference between the arrival of the primary neutrons and the scattered neutrons, that will be around 25 nanoseconds of time delay between the scattered neutrons and the primary neutrons. So that means that our scintillator, the scintillator that's used to detect the scattered neutron, should have a response time that is 25 nanoseconds or faster, so that it's able to detect only the scattered neutrons. And before the next X-ray pulse arrives, that detector would have decayed to around 0 levels. So these, the three important material requirements: there should be a fluorescence or luminescence lifetime of less than 25 nanoseconds, so that the scintillator will have a response time of less than 25 nanoseconds. There should be a high lithium-6 density, typically greater than 10 millimole per cubic centimeter. And of course, the light output of the scintillator should be high enough so that it can be detected by photomultiplier tubes. So the conventional lithium-6 scintillator, which is based on cerium-doped lithium silicate glass that's emitting at 400 nanometers, has a luminescence decay time that is greater than 30 nanoseconds. So obviously, it's not enough to use for detecting the scattered neutrons. So for the new material that we developed, we used praseodymium and cerium ions as the activator ions that produce the luminescence. The main consideration for using these activator ions is their emission wavelengths. We found that the shorter the emission wavelength is, the faster the decay time and the response time is. And so we use praseodymium and cerium as the activator ions. For the host, we chose to use fluorophosphate lithium glass as the matrix. Lithium has to be present because that's where the 6-lithium comes from. And it's also transparent in the UV region. We chose to use glass. Of course, we can use crystals as well, but glasses are more economical to fabricate. So this is the composition of the material that we developed, fluorophosphate lithium glass. It has 80% lithium fluoride content. We use lithium fluoride because lithium fluoride has a high transparency in the UV region, so that will allow the emission from praseodymium and cerium to be transmitted and not absorbed by the matrix. We fabricated the glass using the melt quenching method shown in these steps. And we were able to achieve a high lithium density of 31.6 millimoles, which is comparable to the conventional scintillator, but it's so much higher than the minimum requirement for detecting the scattered neutrons. Right. So using this cerium, so we called our material APLF for short, and we doped that with praseodymium ions and cerium ions. So we characterized the performance of our APLF glass scintillators. In terms of performance, we compared the decay time, the luminescence decay time, with the conventional GS2 scintillator. So for this purpose, we use the californium 252 neutron source as excitation. We can see that for the conventional GS2, the decay time is very long, 39.8 nanoseconds. But also there is this afterglow that is disadvantageous when we're using a material for a scintillator, because we want a sharp response time for our scintillator. We can see here that the response time for the praseodymium dope APLF, which is this black curve, is very fast. It's 5.3 nanoseconds. It's one of the fastest scintillators that has been reported. For the cerium doped scintillator, it has an intermediate decay time of 28.9 nanoseconds. So in terms of decay time, the praseodymium APLF scintillator is superior to the cerium doped one and the conventional scintillator. In fact, investigating the decay time using different rare earth ion activators as dopants, the decay times are still so much faster than the conventional scintillator. Neodymium ions would give us the fastest decay time, and that's also because neodymium gives the shortest luminescence wavelength, which is around 172 nanometers in the vacuum ultraviolet region. But still we chose praseodymium because it has a fast enough decay time, and at the same time the luminescence emission is in the ultraviolet region. So comparing the performance of the scintillators in terms of the light yield, we can see here this is the conventional scintillator, has a very high photon yield, so much higher compared to our APLF scintillators. But focusing on our APLF scintillators, we can see that cerium, doping with cerium achieves a higher photon yield compared to doping with praseodymium. So sure, we can get a very fast response time with praseodymium doping, but that sacrifices the photon yield. If we dope with cerium, we get a high light yield, but that also sacrifices the decay time. So the decay time is longer for cerium. But for us, the decay time is a more important factor because we can always fabricate a detector with scintillator arrays. So that's what we did. So we took the praseodymium, which has the faster decay time, and we fabricated a scintillator pixel array using strips of a praseodymium dope APLF. By using this array, we are able to integrate the scintillation light yield, so that even if a single single scintillator has low light yield, the combined light yield will be enough for us to detect the luminescence intensity. So using that scintillator array, we were able to successfully detect the scattered neutrons during nuclear fusion. So these are individual measurements from individual arrays showing the primary neutrons and then the weaker downscattered neutrons. But if we integrate these the signals, we can come up with more discernible curve showing the primary neutrons and clearly distinguishing the scattered neutrons from the primary neutrons. But more experiments are now ongoing, and despite the success of praseodymium dope APLF, still more work has to be done. So now that we have successfully grown rare earth ions doped in APLF glass, we now have to improve the performance of, especially with the light yield, the photon yield, and the efficiency of the scintillator. So we are looking at 3 approaches to do this. We can either control the concentration of the dopant ions, or we can co-dope our APLF matrix with both praseodymium and cerium. And we can also look at other rare earth ions such as erbium or neodymium, as I've shown earlier in the slide. But in this talk, I will discuss the results on co-doping with praseodymium and cerium. As I've discussed earlier, cerium has a high light yield and praseodymium has a fast response time. So by co-doping with praseodymium and cerium, we are hoping to leverage the advantages from each of these ions and come up with a better scintillator. So this figure shows us the absorption spectra of the co-dope praseodymium and cerium co-dope APLF glass. So we see these characteristic peaks coming from praseodymium. We are also able to observe the absorption edge of cerium and absorption edge of praseodymium. And doping, so increasing the amount of cerium in our glass shifts the absorption edge to shorter wavelengths. So we are able to essentially control the absorption edge. Looking at the emission of our co-doped glass scintillator. So this solid blue line shows the photoluminescence emission from the praseodymium ions when they are excited by wavelength shown by this photoluminescence excitation curve. So the solid line is the luminescence emission. The dashed curve shows the excitation spectrum. So for us to excite the praseodymium in the glass matrix, we need to excite from 150 to 200 nanometers of excitation. Then we get this photoluminescence emission from praseodymium. Looking at cerium, so cerium, it's this red curve.
Professor
The red,
Marilu,
yes,
Professor Marilu,
yeah,
please, Professor Marilu, sorry for interruption.
yes,
You have only 3 minutes to finish it. Hello,
sorry,
3
how
minutes are
many?
left.
3 minutes,
You are
yeah,
requested to finish it within
yeah, okay,
3 minutes.
yeah.
3 minutes. 3
3
minutes.
minutes. Yeah, I'm almost done. Yeah, so here we can see the emission from praseodymium, but we can see that the excitation spectrum of cerium overlaps with the emission of praseodymium. So this tells us that there would be some energy transfer from praseodymium to cerium ions. So we investigate the energy transfer further. This is the streak camera image showing the emission from praseodymium and emission from cerium. We can see that for purely cerium dope, we have this decay time. But if we increase the concentration of praseodymium, we see a delay in the rise time of cerium, which confirms the energy transfer from praseodymium to cerium. And indeed, if we look at the luminescence intensity, if we increase the ratio of cerium going from 0 cerium to 1% cerium, the intensity of the praseodymium emission decreases. And that's because energy is transferred to the cerium ions. We also see, as a result of the energy transfer from praseodymium to cerium, that the decay time of praseodymium becomes faster. So the red line is pure praseodymium. The blue decay is with 2% cerium. So we are able to achieve actually a very, very fast decay time of 0.4 nanoseconds. By controlling how much cerium dopant is in our scintillator, we are able to control the luminescence decay time and therefore the response of our scintillator. And this graph just shows us the energy level diagram showing the energy transfer from praseodymium to cerium. Okay, so for future work, we are still looking at improving the efficiency. We will also try our co-dope APLF glass scintillators in actual laser fusion experiments. But essentially, in summary, we have developed fast response lithium glass scintillators based on fluorophosphate lithium glass doped with praseodymium and cerium. And by co-doping with both praseodymium and cerium, we are able to control the decay time and the response time of our glass scintillator. Future work is still ongoing. Of course, questions are welcome, but if you want to know more about our work, I direct you to our recent publication in the Journal of Non-Crystalline Solids and the Journal of Alloys and Compounds. And thank you very much for your attention.
Okay, thank you, ma'am. Thank you, Professor Marilu, for your nice presentation. Very much informative for researchers. And now your presentation is open for discussion. Any query from participants?
There is one question, sir, in the chat box. Which software you use for getting thermal images?
Oh, okay. So the thermal images, that's the strict camera image here.
This software you use getting thermal images. Okay.
Yeah. This is actually not a thermal image. This is the strict camera. This is essentially just a charge coupled device that plots the wavelength and the time in 3 dimension. So it comes with, it's not a particular software. It comes with the spectrometer that's used to detect the wavelength and the response. So any spectrophotometer should have this capability to plot this 2-dimensional plot in color.
Any more query?
No more questions.
Okay. Okay. Thank you, Professor Marilu, for your explanation on the query. And now I would like to invite another speaker to continue our session. The another speaker is Professor Meenakshi Singh from India, and her topic of presentation is MIP sensors for disease biomarkers.
Thank you, sir. Thank you.
Professor Meenakshi. Okay, ma'am.
I hope my screen is visible. Am I audible?
Yes, ma'am.
Okay. Thank you, Professor Pandey, for inviting me. And I would like to thank Professor P.K. Singh and the entire organizing committee to giving me an opportunity for presenting the work going on in my lab. So I am talking about a special class of polymer. So in general, any polymer which a functional imprint given in the polymeric system. So, and this special kind of polymers are called as the molecularly imprinted polymers. MIPs are polymeric matrices prepared with the imprinting of templating molecules. Actually, in simple words, if I would say, while polymerizing the monomers, a small molecule, or it could be a larger molecule, a little bigger molecule, whatever molecule can be added with the monomers. And with the chemical functionality, functional groups compatibility with the monomers and the molecule which is added, there is a polymer is designed or polymer is developed with the space for that analyte or template or molecule which we have added. So during the growth of the polymerization, if you add a simple molecule, the monomers will arrange themselves around that molecule, and ultimately the polymer, which is after polymerization, the polymer developed has the imprint for that particular molecule. So this technique is being utilized for sensors, and this is going to be a very good, revolutionary and cost-effective technique in near future, and it has already coming up in the commercial scale, but very slower. So we are trying to popularize it by such platforms. So molecularly imprinted here in this picture, which I am showing here, you can say template, which I was referring to as a small molecule. It could be a small molecule. It was actually in the starting of the MIP field, it was a small molecule, but now it has developed to a larger molecule. It has been tried for biomolecules also. That is what I am going to present here today. So with the functional monomers and template and the cross-linking monomer, before polymerization, this pre-polymerization complex or pre-polymerization solution is prepared. If it is in the solution phase, generally polymerization occurs in the solution phase. So the monomers and the molecule, with the cross-linker, they are self-assembled around the chemical functional groups of this. And on giving the polymerization initiative, with the help of cross-linker, this polymeric matrix is developed. And if by chemical or physicochemical means you from the a little rigid polymeric matrix, if you extract this molecule, the space left out here in the polymeric matrix is actually the imprint of this template. So this extracted, or this polymeric matrix from where the molecule template has been extracted has a imprint, and you can use this as for sensing in any other matrix. So imprinting process includes self-assembly process, implicating either of covalent bonds or non-covalent interactions between the monomer and the template. Here we are showing it that this functional monomers can form either covalent bond or non-covalent bonds. Non-covalent bonds includes the hydrogen bonding, the electrostatic interactions, the van der Waals forces, London forces, hydrophobic forces, hydrophilic forces, and a lot of non-covalent forces which are responsible for biomolecular recognition. So here this molecular imprinting concept is biomimicking the natural recognition systems. These matrices means the polymeric matrix, are robust molecular recognition receptors that could be able to serve as natural recognition entities such as antibodies and biological receptors. So just to say, or the way in which our biomolecules, the enzymes and substrate function, in a similar manner, this also functions. Actually, our enzymes are also polymers. They are polymers of amino acids. They are basically proteins. So there also they have the specific cavity for selecting only and only the substrate. So here also we can say that this is the polymeric matrix which has the specific site only and only for the recognition of or sensing this molecule. So this is the molecular imprinting technique. A little more about this. This polymeric matrix, which I call MIP here, with its imprint. When you extract this molecule, it has the imprint. It can be used as a MIP sensor, and it is being used in the literature, in the laboratory scale. This has been utilized for sensing the drugs, so sensing the food adulterants, for sensing the various pollutants, atmospheric or the hydrospheric or whatever pollutants are there, and the protein molecules also. So the title of my talk was for disease biomarker. So I will present the work from my lab, and that is for the protein imprinting. I mean, for sensing the protein from the various bacteria or any other biomolecule which is a disease biomarker for certain disease. This MIP sensor can be designed for that protein, and it would give a very good commercial sensing device, which is very, very cheap. It is actually it is coming up as an alternative to the biosensors. Biosensors means in the biosensors, the biological elements are present, When I say biosensor, if suppose I'm making a biosensor for urea, then the people, the scientific people, the science, the people from biosensing fraternity, they generally immobilize urease enzyme. Urease enzyme is highly specially specific for the urea. So they are preparing the urea sensor by immobilizing the urease enzyme. So similarly, we are here giving a MIP platform for sensing a particular molecule. So the thing is that we can design the particular MIP sensor for any kind of molecule, ranging from the drugs, food additives, pollutants, proteins, and many more. So at the laboratory scale, it is very successful. And now this fraternity, MIP fraternity, wants to take it to the commercial scale in the market for diagnosing the diseases. Because biomolecules, urease enzyme, keeping it at convenient temperature, pressure, and under special conditions is very difficult. But the chemical sensors, MIP sensor would be a kind of chemosensor, chemical sensor. So keeping it in the lab or keeping it at any store is very easy. It is stable at the ambient temperatures. So for today's talk, I have taken a special disease called typhoid, which I will deal in the later slides. So the objective here is to design MIP sensing platform for disease causing bacteria. The bacteria, we are developing the MIP sensor for a protein from bacteria. So once you are sensing protein from a specific bacteria, then bacteria is also being detected. So we are, if the bacteria is present in our biological fluids like blood plasma, etc., or urine, etc., then we can say that yes, this person is infected with this disease. So the objective here is to design this MIP sensing platform for disease-causing bacteria in a single imprinting platform. A single electrode will be designed for sensing this bacteria with good selectivity and sensitivity. Or I can say the selectivity and sensitivity at par with the enzymes or our biological proteins. So how it would be done? So it's you all are people are from the polymer field. You are very much familiar with the electropolymerization. Electropolymerization is a very conducive and easy technique for this. So here, for electropolymerizing, the 3 electrode system would be there, and we can use carbon-based materials or any other electrode also with a suitable conductivity, etc. And on this electrode, this imprinting matrix would be immobilized or electrodeposited, or electropolymerization will be done on the electrode itself. So this imprinting matrix can be generated on the electrode itself, and this can be monitored here. In a more simplistic manner, I will show you how this particular MIP will be, which we are using for this particular disease causing bacteria of typhoid is here. Here, this is the schematic picture of electrode. The template means for the protein or the peptide for which you have to prepare your MIP. And this is the functional monomer. So this template is present with the functional monomers here. And this cross-linking monomer is also there. The cross-linker is also there. So template, cross-linker, and monomers, functional monomers, 3 things are there. They are self-assembled and then electropolymerized. The monomer will be capable, will be electroactive, and it should be capable of electropolymerizing. Otherwise, also, if the monomers are not electropolymerizable, then also we can electrodeposit them by other means. But here we are using the electropolymerizable monomer. So they will be electropolymerized on the surface. So as I have shown in this figure here, this would be the polymerized thing, immobilized on the electropolymerized on the electrode surface. And then we can treat this by different physicochemical means to extract the molecules. Being a chemistry faculty, it's very easy to play for us with various solvents and other means to extract this template molecules. And then this polymeric matrix deposited on the electrode is left with the imprinted cavities for this template. Now you take another solution or you can take your biological fluid, you can take the river water, whatever you want to test that whether this molecule has this template, this solution has this template molecule or not. You only expose the solution with the electrode, and you see these are the interferent molecules. Interferent means other molecules which could have similar property than the template molecule for which you are preparing the sample. So in presence of all this, the imprinted cavity will take only and only this. While working with the small molecules, the scientists have seen that even if you are preparing the sensor for R configuration, even it is not taking the S configuration, just like the enzymes. So it's highly successful. So with this schematic presentation, I'm going to present this. And here for this work, we have taken a special, or being most of the people are from material science, they are familiar with the piezoelectric technique. So we have taken a quartz electrode. Quartz is a piezoelectric material, and on that quartz electrode, a gold film is deposited, and on that gold film, deposited on the quartz disc or quartz electrode behaves as the electrode here, as a working electrode. So if you keep a counter electrode and a reference electrode, this functions as a 3 electrode system. So on this gold electrode, we have immobilized or electropolymerized our imprinting matrix, and this. So this piezoelectric, we call it as EQCM. EQCM, electrochemical quartz crystal microbalance. It is being provided by all the suppliers like Metro, Autolab, and CHI, etc. So it can monitor the electrochemical happenings or the things going on, as well as the piezoelectric things. So for determining the electrochemistry, we all are familiar with the things, but for the piezoelectric things, there is a special Sauber equation that the resonating frequency of the quartz electrodes is defined by this. You can see here delta M. Keeping all these things are constant for a particular setup, experimental setup. The delta F means the change in the resonating frequencies is dictated by this delta M. So if something is being deposited on the quartz electrode, its resonating frequency decreases. You can see here the minus sign. With the deposition of the mass on the electrode, on the quartz electrode, the resulting frequency is decreasing. And if something is being released from the electrode, some material is being lost by the electrode, then this delta M, with this delta M being positive, the frequency of the resonating frequency of the quartz electrode increases. So with this introduction about the electrode, with this EQCM setup, simultaneous study of electrochemical as well as piezoelectric behavior is possible. Extremely sensitive mass measuring device. Yet this delta M, if it changes by a few nanograms, then also delta F changes. So you can monitor the nanogram changes. And it allows dynamic monitoring of chemical interactions. Dynamic monitoring means if something is being added, then the delta F changes, something is being released, then also delta F is changing. And simultaneously, the delta R, the resistance of the electrode, allows us to monitor the viscoelasticity of the coated film. Viscoelasticity means if your deposited film is rigid or it is very loose. You can understand this. So by monitoring the frequency of the quartz electrode and by monitoring the resistance of the quartz electrode, we can get much information about what chemistry of physics is going on there. Any binding of mass on quartz crystal, resonating frequencies decreases. Any release of mass from quartz crystal, resonating frequency increases. So with this background, what I'm presenting the work we have done in our lab. Recently, not recently, but recently it was came into light more due to the COVID pandemic. But earlier also, the diagnosis of typhoid was very complicated because it has, when the patient is not infected, then also sometimes the pathology labs that give positive result. We call it false positives. Biology people, medicine people call it false positive. And it has overlapping symptoms with other diseases. The symptoms which are occurring due to the typhoid is common to other diseases also. Even with the COVID-19, we have seen few cases in the COVID-19 that the patient was diagnosed with typhoid and the typhoid treatment was going on, but the patient was not responding. And then later on, they went for the COVID test, and it was due to the symptoms were due to the COVID, not due to the typhoid. Vidal test, which is popular for the typhoid, is also has not really specific. So typhoid, and typhoid is common in Asian countries and African countries. So you can understand being poor, poverty is common in these countries. So pharma people are not interested in developing the, because pharma people, I'm not accusing, but I'm generally discussing, is generally saying that they only go for the market driven, this money-making devices. So for the typhoid diagnosis, it is being ignored. So here we are trying in our lab to diagnose typhoid by using the MIP electrode. Typhoid is developed due to the gram-negative bacteria, Salmonella typhi. And so from this bacteria, a bacterial tip protein. And yes, before starting this, I would like to tell you that for this work, we have taken the help. We have gone into invaded a new field called as the bioinformatics or immunoinformatics. So we have used this immunoinformatic techniques available on various servers provided by bioinformatics people for predicting a peptide sequence. For this, from the Salmonella typhi bacteria, this bacterial tip protein, Salmonella invasive protein B, called as SIPD, was shortlisted for immunoinformatic studies. This bacteria has many proteins. This bacteria has many proteins, but we would like to choose only one protein for detecting the bacteria. So this Salmonella SIPD protein was shortlisted, and by using these different immunoinformatic tools, IEDB and many other Vaccine and ABC Pred, various other tools are available on the bioinformatics sites. From there, we have taken a predicted, you can say extracted or not extracted, biologically not, it was all in silico work. So we have, you can say, taken a peptide sequence which was 14 amino acids long. And this 14 amino acid protein sequence was called as the epitope peptide sequence. Epitopes, the biology people know, it is very specific to a protein. The epitope is a sequence of protein, peptide sequence, which is unique to that protein only. That sequence of peptide is not present in other proteins of even that bacteria. So by using this bioinformatics and immunoinformatic tools, we have extracted not extracted, extraction is a word for wet lab. This is in silico work. We have taken a epitope peptide sequence. This was predicted. It was anticipated as one of the most suitable antigenic peptide sequence of protein SIPD. By commercial companies, we designed that. This work is unpublished, so I am not detailing the sequence. It has been submitted to the journal. So without giving the sequence of the epitope peptide, what we did, we tagged a cysteine amino acid at the end. Cysteine has sulfur, and sulfur does the thiol chemistry is very good for development of self-assembled monolayer on gold surface or silver surface. So here we have exploited that thiol chemistry, and this sequence of the peptide sequence tagged with cysteine and was custom synthesized by a commercial supplier and used as template for constructing MIPs itself. When we tried to develop the molecularly imprinted polymers for entire protein, it was not successful. Not my lab, but in other labs also. Because proteins get deformed or denatured easily by the solvents. So we are not going to immobilize the whole protein. We are going to use this epitope sequence with the 14 amino acid sequence only as a template for, and then mixing it with the functional monomers to electropolymerize on the electron. So this this molecularly imprinted polymer as well as non-imprinted. Non-imprinted means the polymeric matrix without the template. So this functional monomer used was 3-sulfopropyl methacrylate potassium salt, and glutaraldehyde was used as a cross-linker to polymerize on the surface of ICSEM electrode in presence of the template. And this template was the epitope peptide sequence with 14 amino acid residues tagged with cysteine. And this 14 amino acid residue was predicted with the immunoinformatic tools. In overall methodology, I will try to explain this in this schematic diagram. This is the, you can say this is the epitope, or the 3D structure of the okay. This is the symbolic for showing here on the electrode. This is shown as small this, but the 3D structure of the SIPD protein looks like this. Looks like this means we have predicted this. We have used this immunoinformatic tools, Ramchandran plot, etc., to figure out this SIPD protein structure, and our template is being shown here. It is shown here, and this epitope is present here. So what we will call, this is the electrode, this is the quartz crystal, the gold electrode, gold film is deposited on the quartz crystal. This gold film will be treated with the epitope by the cysteine sulfur atom of the cysteine amino acid. These epitope sequences, peptide sequences will be self-assembled on this gold surface, and then the monomers 3-sulfopropyl methacrylate will be added, and the cross-linker will be added, and it will be polymerized on the electrode surface on itself, because the technique is being for polymerization, electropolymerization. So I will show you the CV of the electropolymerization process, and this is called as adduct because this polymeric matrix has these template molecules, has this protein epitope peptide molecules. On extracting this peptide molecules, this is called as MIP, because now this MIP has the cavities to take another set of this peptide molecules or proteins. So via this peptide molecules, means this is the protein, whole protein of the SIPD. Via this, yes, pardon.
Please conclude your talk.
Okay. I will take 2 to 3 minutes more. So by using this, when we are preparing the sensor for this epitope or this peptide sequence, through this peptide sequence, the whole protein will be bound on the gold surface. Okay. So this is the tertiary structure of SIPD protein, which has been developed, predicted by us. This is the CV, which is showing for the electropolymerization of this MIP, and this is for the NIP. And on the electrode itself, when we, for the extraction process, we have used this PBS phosphate buffer solution with the pH 7.3 and with the ionic strength 40 millimolar. And you can see the increase in the frequency. That means here on your electrode surface, the things or the materials are being released. So this is the proof that the extraction is complete. When it levels down, we stop the extraction. And now you can see the binding. This is for the non-imprinted polymer, and this is for the imprinted polymer. So here's the frequency shift. You can see this is 0 scale, and here you can see the decrease in the frequency. That means the mass is being deposited and the corresponding frequency, resonating frequency of the quartz electrode is being decreased. But under the similar experimental things, the non-imprinted polymer is not at all taking anything. So this gives us the selectivity. This is the, as I'm going to set to conclude. So I will, this is the another testing for the cavities being present. Here potassium ferrocyanide as a redox probe is being used. This is the adduct means the MIP with the epitope molecules. It is not being taking any redox probe. But as we extract, this DPV response increases. This shows that cavity is present in the polymeric matrix that allows the redox probe to reach to the electrode surface. This is the interior spectra. Here also you can see the similar things. And here, this is the here we have determined the surface area of the electrode for the NIP electrode by using the Randall-Sevick equation, by plotting the peak current of this CV with the square root of voltage, square root of the scan rate. This is the 3D figure of the AFM image. You can see here, this is the MIP and this is the NIP. Non-imprinted has simple blank surface. Very few polymeric things are being shown here. But here you can see the non-imprinted after extraction. You can see here the scale, the nanometer, 200 meter. You can see easily that 200 or 250 nanometer depth cavities are being created on the surface. And this is the most USP of our work, that we tested this with the other interference. These all are the other peptide sequences. GW10 means the peptide sequence with 10 amino acids, with 14 amino acids, with 13 amino acids, CoC14, 13, and etc. These are the aspartame and this carnosine available. Carnosine and aspartame are dipeptides. You can see none of them are being are binding to the polymeric matrix, as the frequency, resonating frequency, is being shown in the positive side, means they are being released. They are only the thing which is binding is our epitope molecule. You can see this is the, in the scale of 10 to the power 3, is 15,000, minus 15,000, and they are not even responding to a single positive frequency. So this is our USP, that the prepared electrode is selective and specific only and only for the peptide sequence for which we have developed. This is the our resistance being shown here. So you can see the viscoelasticity in the other, the viscoelasticity in these with the other interferent molecules is too high. They are not binding. They are fluid, moving like fluid, like anything. But here the scale shows that is very low for the our electron. This is the calibration plot for the epitope sequence. In analytical chemistry, if you are giving a sensor to the at the commercial scale, you have to show that what is your detection limit. This is our detection limit in nanogram per ml. You can see it's very low. And what is your linearity range? So this is our linearity range. The equation is shown here. Yes. Now, lastly, we have tested it with the patients from our hospital. BHU hospital has huge load of typhoid patients. So Professor Gopal Nath from the IMS, Institute of Medical Science, was kind enough to provide us the patient, sample from the typhoid infected patient. You can see this is the sample from the healthy human being which do not have typhoid or any other disease, and this is the sample.
Professor, excuse me,
yes,
Professor,
just 1 minute. This is the sample from our lab. This infected patient, and you can see the binding here in the negative side, and it is reproducible almost after 1 month also. So it's a huge success for us, that although many proteins are present in the blood sample, you can understand in the healthy person blood sample, many proteins are present there, but none of them are being bound to the polymeric matrix, and only the infected blood sample is given. That means the bacteria present in the patient's blood sample the protein from the bacteria is being detected by our polymeric matrix. So here I'm concluding this same things, that this can be used as an alternative method, as a diagnostic tool for typhoid. And this is the future prospects for the MIP. MIP has a very good future prospects. Materials can be used as sensing device for anything, as storage materials, as microreactors for cryosynthesis, catalytic converters, and very in this pandemic period, we have realized the huge cost of the testing, the medical cost effective, very cheap medical devices, diagnostic tools can be done. This is the students from our lab. The bold ones are who contributed in this particular work. and this is the funding. Thank you.
Session is open for discussion. If any query from participants.
Yes.
The discussion is open for questions. We can accommodate one question. So we can move on to the next talk, sir. Professor Pandey, we can move to the next talk.
Thank you for giving the opportunity.
Yeah, thank you so much, Professor Singh, for your nice presentation. We were running short of time, that is why we had to interfere. Professor Pandey, there is a lag coming from your side, sir. Okay, so maybe the network issue is there, that is why. Okay, so we will invite the next presenter. The next presenter we have with us is Professor Jai Singh. He will be giving his talk on metal dichalcogenides, nanomaterial for transistor application. Professor Jai Singh from India. Sir, we invite you to make your presentation, sir. Professor Jai Singh, we are not.
Yeah, can you hear me?
Yeah, we can hear you and see your presentation. Please make it full screen, sir.
Okay, wait.
Yeah.
Okay, just give me. Okay, okay. Now I can start.
Yes, sir. Sure, sir.
Okay, thank you very much. Very good morning, and
Sir, lag in the audio, sir. Professor Jai Singh, we cannot hear. We are not getting your audio. Dr. Sunil Chauhan, can you kindly check?
Ma'am, I think there is some problem in their speaker or their mic.
So can you take out your microphone? If you are using a microphone, there can be a lag. He has logged out, I think.
can you hear me?
Yes, we can hear you now.
Yes.
Pari, देखो ये आवाज नहीं आ रही.
Sir, we can hear.
Now,
we are getting the audio.
आवाज नहीं आ रही.
Now, sir, we are getting the audio, sir.
बंद करो उसको बंद करो. उसके चक्कर मत पड़ो मैं कह रहा हूँ. हाँ तो फिर आ क्यों नहीं रही इसमें?
Sir, we are getting your audio, sir. We request Professor Jai Singh to make his presentation. Professor Jaising.
Hello, can you hear me?
Yes, sir, we can hear you, sir.
Okay, thank you very much. Basically, some problem in my microphone. So due to that, I cannot wait. I'm going to connect my slide. Can you see my slide?
Yes, sir, we can, sir. Please continue.
Okay, thank you very much. Very good morning and namaskar to all. First, I would like to thank the organizer to organize a wonderful conference at the virtual platform. Special thanks to Professor R.C. Singh and Professor P.K. Singh for his kind invitation. Today, I am going to discuss about this is the transition metal dicarbonate materials and its application in a transistor devices. Before they start my talk, I want to acknowledge my mentor and my collaborator in SUITS and DST and UGC for they have provided the fund to start my work in that. These are my collaborator universities and institute in a various country. Basically, recently we got the one project in the collaboration of the Technical Institute of Sofia, Bulgaria. International Pro, and these are my publication which I have published in different journals. My H index is nearly 28 and I10 is 52. This is my brief introduction. That as we know that the first two-dimensional graphene material was discovered in 2004. After the discovery of the graphene, several two-dimensional materials have been synthesized by the various groups and by the various methods. The two-dimensional materials, especially transition metal dicarbonites, have gained a worldwide attention in recent years for the possible application in the energy storage as well as the in transition-related devices. It is a wonderful materials that could be transformed the material science world. I can say the TMDC had a certain important advantage over silicon materials, especially MOS2 device, 3 times smaller than silicon. For a silicon-based transistor, we need 2 nanometer thick, but in the case of MOS2, 0.65 is thickness is enough for the electronic devices. Means this is the MOS2 is a 3 times smaller than this silicon devices, and due to this this is a lower thickness, we consume the less electricity, and this is we can require the very minimum area for design this MOS2 devices. Most importantly, MOS2 can tune in a indirect to direct band gap in a visual region, and MOS2 seems to be the better alternative than silicon for the various electronic edge future gadgets. Nearly 40 types of different layered TMDC compound exist in the natures. They have the different electronic character with the different layers. And the important thing is that they have the showing the metals, semiconductor behavior, and superconductor and semi-metal behavior. Metal behavior, this is for example, titanium sulfide and VSE2. And for semiconductor, there are several semiconductor compounds are existing in this dicarbonate, MOS2, WS2, and MOSC3 and WSC3. There are several types of TMDC exist in this. And that is the basically important thing is this basically TMDC exists in testing band structures with a tunable band gap. We can easily tune the band gap from 1.2 EV to 1.8 EV. That is very important. Due to that, the material is very good for the for transistor other things. The band gap is one of the most important factor in the two-dimension for determining the property and application. For this, in particular, in the I am talking about the graphene. Graphene is a semi-metal with a zero band gap. So that is the due to that the graphene has the several limitation in electronic and the photoelectronic devices. Basically, TMDC exists a variable band gap from 0 to 3 eV, which can be tuned by the thickness, defects, dopant, and also mechanical deformation, as we know very well, with the help of tensile strength and compressive strength. The most studied semiconductor is the TMS2, MOS2, and WS2. So today I will describe my whole the talk on that is the MOS2. This is the first report on the two-dimensional dichloride materials. Basically, I'm talking about the two-dimensional. That is very earlier MOS2 and WS2 was synthesized for the solid state lubricant materials. But in 2000, after the discovery of graphene, the same group has Andre James and Nobleswa has they have synthesized by the micro mechanical explosion methods, and that time the mobility is very low, nearly 3 centimeter volt per second. The mobility is very low in the especially on MOS2. Why MOS2 is very important? Basically, this is the important thing is the crystal of the MOS2 was composed the vertically stacked. Basically, two MOS2 layer is the weak that is interact with the weak van der Waals interaction. An important thing, as I told you, this is the in a MOS2 bulk is that band gap is 1.2 indirect band gap. But in the if you talk about the this is the in a monolayers is a band gap nearly 1.9 eV is the direct band gap. So due to that is the material can be used in the field effect transistor and photo detector, as well as that is good for the storage. This is the lithium ion battery and super capacitor. We can use this material. And why I am interested in this is the MOS2 for a nanoelectron is basically this is the important thing is that is the stability of this materials in air is the nearly that material is stable at a 400 degrees centigrade in the air condition, and also stability is very high compared than any silicon and any other materials, as nearly 700 degrees centigrade that material is stable in argon. And that for any electronic devices, if you think about the most important property is on-off ratio. On-off ratio is very good compared than any other semiconductor and any other semiconductor materials. And as well as the mobility is very basically mobility is graphene is very high, nearly 10 power 5 centimeters square per volt per second range. In case of the this MOS2 mobility is nearly 200 to 1000 centimeters. Different group was reported different methods, and then I will describe my talk in the basically on two methods. First I will describe the CVD method, and next I will describe about the sputtering method. Then we will compare with our result with two different methods, and then we will check the mobility and other things. That is the important thing. The most important thing is that basically due to the stacking of the layers along the C-axis, this is the space group of the PC3MC, and due to several type of polymorphic crystal structure existing in the TMDC, and this is a common 4 types of TMDC exist in the MOS2. This is a 1H, 2H, and 1T, and TD, and 3R. This is H is that is the hexagonal type structures, and T is the trigonal type structures, and TG is the distorts or octahedral structures, and R is the rhombohedral structure. But common structure is the 2H and 1AH. Due to that, this is the important crystal structure of molybdenum disulfides. Take in the form you can see here. This is the hexagonal pattern of this looks like S atom. On either this is the upper layer is this is the sulfur, and that in middle that is the molybdenum, and that is between two sulfur that is molybdenum sandwiches type, and due to that, and that another layer is connected with a weak van der Waals, but with MO and sulfur that which attract with this is connected with the strong covalent bond. Due to that weak van der Waals, we can usually use this material, and we can usually, that is, remove this material with the mechanical cleavage. So easily that can be synthesized better this mechanical cleavage. But important thing is that that is as we know that the mechanical explosion methods provide the purest any MOS2, WS2 or graphene films, but the sample size is very extremely limited by this exploited methods. Basically, in this work, I will discuss about this MOS2 film synthesized on silicon oxide and Saphira substrate by CVD methods. This work is published in Journal of Allied Compounds. For this CVD methods, we have used the two steps, two zone furnace, and that is one is the lower zone for zone, and other is the higher zone. Is a lower zone, we are putting our sulfur sample powder. Sulfur is melting point is very low, nearly 120 degrees centigrade, and other zone is this is a MO3 powder. That MO3 melting point is very high, but we have used the basically vacuum system. This is a vacuum base nearly 10⁻²TARs, and that and near to this MO3 powder, we are putting our substrate, silicon oxide substrate, and that whole reaction we will take in is the different temperature and different times. Most important things, we have did a lot of experiment for this. We have selected the different amount of sulfurs and different amount of the MO3 powders and different temperatures. So we have selected the sulfur amount 0.2 gram to 0.3 gram, and MO3 powder is amount of 0.2 gram to 0.4 gram, and temperature 600, 650, 750, 850, and so on. So we have taken a lot of things here. So there is several parameters we have selected here. So finally, we have with the help of this parameter, we have found the different layer of the MOS2 layers. So first we synthesize this materials, MOS2 materials, in the presence of sulfur powder. At that, with the help of this temperatures and flow of basically we are not variable. The organ flow is we are the whole experiment during we are fixed nearly 100 SCM, but only we are varying the amount of the sulfur and amount of this MO3 precursor, as well as the temperature of the high zone furnace. Not we are and low as sulfur temperature we are not changing. We are putting the same sulfur powder at a low temperature zone, 120 degrees centigrade. So that is the this is the high temperature we are using system. This is MO3 powder is the initially reduced by the sulfur. This is the form in the volatile form of the suboxide of the MO3 3-X. And after this MO3-X in the presence of sulfur, that will form the purest form of the MOS2, and that form of the that another form is the gaseous form that will be removed. That is the whole. This is a whole reaction likes in my present work. And this is the optical image of the MOS2 film layer deposited in the different time, different temperature. And initially we have find that this is the monolayer film we have observed as the 650 degrees centigrade, and bilayer is the nearly 700 degrees centigrade, and multi-layer film we have find the 800 degrees centigrade. For this confirmation, we have taken the Raman measurement and also XRD measurement. This is our Raman spectra of the samples. And basically here we are showing that is the amount of the sulfur is very important in my whole this work. That when we are taking the very less amount of the sulfur, 0.1 gram in the sulfur, that is expanded at the 600 degrees centigrade, that we have found that there are several other peaks are observed in this our Raman spectra. When that is the that we are going to increase our amount of the sulfur, that finally we have found the very good quality of MOS2, and this MOS2 film is as like a standard as like the as reported is the monolayers as well as the. So that is very important, is the sulfur precursor amount as is very important in our case. So this is a XRD spectra of the MOS2 is the different amount of sulfur content. As such, we are taking the 0.1 gram sulfur, 0.15, 0.25, that we are find the same thing, that we are taking this very lower amount of sulfur that is found with some other peaks is as also some that is called of the some impurity peaks. This is AMO3 peaks and other peaks is also observed. But we are taking our sample is the sulfur amount is 0.25. Then we found the very high crystalline, high good quality of MOS2 peak are observed. This is along to C axis, that is 002 lattice orientation. This is called the C axis orientation. So that is very good for the. This is the good for this is the stacking layer structures. This is good for the our electronic devices, other things. For a detail, this is for then we are also I told you this, I have taken also the temperature dependent. Then we can see here when initially when we are taken the 600 degrees centigrade, there is no formation of the MOS2. Then we increase the temperature of our substrate, then we get the nearly 650 centigrade. Then you can see this is a clear cut MOS2 is observed. There are two characteristics peak, that is the E12G and A1G. That is the related to in plane and out of plane vibration. I will describe in my next slide. And that we can increase our the temperature of the substrate. Then we could find our that is the system is going to FWHM of this Raman spectra is going to increase, and that also the layer of the simple layer of the thickness of this MOS2 is going to increase in this when we increase the temperature. At there is 650 degrees centigrade, we have found this mono layers, and 750 degrees centigrade we are found we are observed this is a bilayer type of structures, and that is the above them the 650 that 850 degrees centigrade we have observed that this is looks like this multi-layer MOS2 films for that is the we can see here that this is the high resolution scanning micrographs of this MOS2 that is grown at different temperatures that we have observed as 650 degrees centigrade, very very thin and very that we increase the temperature of our substrate, then is the that is the system is agglomerated, and this is looks like the larger grain size of our the MOS2 films. And this is the important thing.
Sorry for the interruption.
Sorry.
Sorry for the interruption. You have to conclude your talk within 2 minutes. Hello.
Yeah.
Yeah, sir, conclude your talk within 2 minutes.
Okay. Okay. Basically, I have completed only one part. Okay, thank you. No issue. One of the most important one tedious things of this is a CVD system. Then we synthesize with the help of CVD. That is a transfer of the film is very important. If you utilize that simple for your transistor devices, any devices, that is make very difficult to that. So for this purpose, we are quoting our MOS2 as grown simple is the PMMA, and after that we are shifting in a EHF that is easily peel up our substrate, and finally we have deposited on our as grown silicon signal oxide for the devices process as well as for the if you want to know your detailed structure for HRTM image, so that is the HRTM image as a synthesized sample. This is as synthesized sample is the in a CVD we have found several types of defects and impurity in the sample. That is very bad thing or a very important observation. That but if you synthesize our sample by the sputtering techniques, that there is no defects. That is we found the very high quality and high quality sample. For a this is our then we have our sample we are for make the that is the transistor devices. That is that we can see here. This is the optical image of our transistor devices. We have used gold and titanium as a electrode here. That you can find here that there is mobility is not good, but mobility of our sample is for the monolayer 7.6 centimeter square per volt, and for the bilayer is very low, nearly 0.8 centimeter square per volt. But in the CVD system, there is in a CVD system you have taken the two types of things. First we deposited YaMO3 and then we are sulfurized by the in the CVD methods. Then we found that this system is a very good quality of our samples, and that with the clearly we are also taken the amount of the sulfur is very important here, and that we found the very good quality of very controlled manner of very large area. That is the good that we can make the very good device. Basically we are not transferring our sample for the further we are using the direct our sample for the transistor device and other things that we can see here. This is the latest fringes of monolayers of basically in this techniques we are first deposited is the YaMO3, yeah, YaMO3 layers. That I'm concluding. Please give me one more minute. After that we are going for the make the devices. Then we found the mobility is nearly to 100 centimeter. That is another. We are directly use the YaMO precursor, YaMO2 target for this system. That in this then we find the very good quality of films, and that film is then we make the devices, and finally we got the very good result in this. There is another reported in this area. So this sputtering techniques is very important for the synthesize this YaMO2 layers and control manner. There is several parameters you can choose. There is time and temperatures and base pressure. So that we have taken here. So this is some publication, important publication which we have published in this area. And thank you very much given the time. Sorry for some problem in my side.
Okay,
Yeah.
thank you, sir. Thank you for your nice presentation on metal dichalcongenite nanoparticles for transistor applications. Okay, have any query from audience side? Hello.
So there is no question in the chat box.
Okay,
Thank you.
Sir, Professor Singh, I have a query. Can this film be used for the photovoltaic application also? Because
yes, sir.
it is semiconductor
Yeah, basically that is also people are using for photovoltaic.
So what will be the efficiency we can achieve from this one? Can it be substitute for the silicon?
Basically not substitute of silicon. Basically that is not substitute of silicon, but basically good thing is this materials, as you know very well. Basically you did a lot of work in solar cell. This band gap is nearly we can tune nearly 1.12 to EV to 1.8 EV. So basically that material you used, basically people are trying about photodiode and other devices. But problem is this materials, that is the that material is not well connected. We cannot make a something we can this is the problem is with interlaying of some other system. Means for we know very well this for solar cell devices we knew several Al2 3 layers, and that is some other contact devices and other contact material for this. So that is problem with. But as for the photo detector, that is a good material for YaMO2 especially. MS2.
Okay, because of the sulfur. Thank
Yeah,
you,
yeah.
sir. Thank you. Okay, sir, for nice clarification. So I would like to invite another speaker. That is, he is from India, Dr. Deepak Kumar. The title of his talk is Current Status and Future Prospects of Polymer Gel Electrolyte for Sodium Sulfur Batteries. So, Dr. Deepak Kumar.
Sir,
Hello.
Sir, thank you very much.
Dr. Deepak Kumar. Oh, yeah, yes. Okay, over to you.
Can you please hear me?
Yes, you are hearing.
Okay.
You are audible, sir. Continue, please.
Thank you. Thank you. I thank the organizer for giving me the opportunity to speak on the topic. So I'm working at Electronics and Mechanical Engineering School, Baroda. This is a AICTE approved institution under Gujarat Technical University, Ministry of Defense, Government of India. So I shall be speaking on the development of electrolytes, especially for the metal sulfur batteries, the lithium sulfur and the sodium sulfur batteries. So emphasis will be especially on the sodium sulfur part.
Excuse me, Dr. Deepak, we are not getting a title slide.
Okay, you are not getting the slide?
Although you are sharing something, but it is not the title slide. It's showing the blank one.
Actually, slide is not visible right now.
Could you
yes,
please check now?
Yeah. Yes, it is visible.
Now it is.
Zoom in. Okay.
Now it is okay?
Yeah. Again, it has gone.
No. Zoom it in full size, full screen. Okay, try to zoom it in full screen.
Yeah. Is this okay?
Yeah, slide is open, but it is not in full screen. Okay, try to again. Try to share it again. Okay.
Because better.
Yes, sir.
Yeah, it
now
is quite.
Now you can make the slideshow. So PowerPoint, sir.
Yeah. I clicked it is processing. Yeah. Could you please see now?
So make it full screen slideshow.
All right.
Yeah.
Thank you. So this is how I have organized the presentation. So some background and then polymer based electrolytes, sodium sulfur batteries, and some investigation on the polymer electrolyte, prototype sodium sulfur batteries, and way ahead. So all of you already know that the fossil fuels has captured the market and 80% of the energy requirements are fulfilled by the fossil fuels even today. So, and fossil fuels are basically costly, problem causing, and they are exhaustible also. Therefore, there is a requirement to investigate other systems. Apart from that, if you think about the sulfur is a byproduct from the gas and oil industry, and its oversupply is projected in the coming future. So to have a balance, check and balance of the sulfur, there is a great scope to utilize this for various applications. The conventional applications of the sulfur is in pesticides, fertilizers, pharmaceuticals, etc. And as an active material, they are used in lead acid batteries as a sulfuric acid. And these days, the metal sulfur batteries are also utilizing a great amount of sulfur. If we see the key aspect, then single year production supply, which is approximately 60 million tons, this is enough for 1 billion electric vehicles with 40 kilowatt of the batteries. So this is having a great potential to be utilized. And the chemical cost of the sulfur based systems is very, very low as compared to counterparts. You already know that lithium ion batteries are the most favorite, and they have captured the entire market, and Nobel Prize of 2019 has been awarded for that. And this prize is shared by three men. So one is this M. Stanley, and he's basically told us that cathode, if we take the titanium sulfide, then it is having some pores at a molecular level, and these are basically creating a pathways for the movement of the ions. Further, the good enough is also who shared the price, and he has predicted that cathode would have been having more potential if we are using a metal oxide instead of the metal sulfides. So he has given this this concept, and he also told that intercalation will be good, and voltage more than 4 volts can be produced. Third scientist from the Japan, his point of view was that in place of using the problem creating lithium, one should use the petroleum coke as a carbon material for the anode part. If we see the timeline development, lithium-ion batteries have reached to the current stage from the smaller application like watches, then cell phones, laptops, smartphones, the cars, and now for the grid storage systems also. So huge development has taken place. But lithium-ion batteries are not ultimate. Although there are some advantages like energy density is high, operating voltage is also good, cycle life is high, wide temperature range of operation, but limitation like flammability, transportation, and shelf life are the issues. Now the question is, what are the choices? The choices includes the room temperature sodium batteries, proton batteries, graphite batteries, potassium ion batteries, the magnesium batteries, and so on. So various choices are available. From the Ragon plot, you can see that the EDLCs are having the highest energy, the power density. If we look at the specific energy densities, then what happens is sodium sulfur batteries are occupying a good space. Electrolytes are integral part of batteries, and they are heart of the battery system. And the electrolytes can be aqueous, they can be organic, they can be solid, and there can be other kind of systems. The limitation of solid electrolyte and the liquid electrolytes includes the solid electrolytes are having inferior ionic conductivity, the transport number is also low, the viscosity is high, and flexibility is less, so interfacial contacts are poor. And liquid electrolytes, on the other hand, they have issues like leakage, transportation, flammability, and corrosive nature. Thermal stability is another issue with such kind of systems. So that's why the people are trying different kind of polymer electrolytes. The polymer electrolytes can be of like polymer salt complexes, plasticized electrolytes, gel polymer electrolyte, and composite polymer electrolytes. In this presentation, we will be focusing on the gel polymer electrolytes and some investigations on that. Polymer gel electrolytes are the membranes which are having transport properties quite comparable with that of the liquid electrolytes, and such electrolyte is formed by the dissolution of salt in polar high electron solvent and adding a neutral polymer to achieve mechanical stability and good conductivity. Utilizing a polymer gel electrolyte for sodium sulfur batteries, the specific advantages includes the conductivity is good enough, the transport number is also high, and they are leak proof, non-aqueous, flexibility is good, and you can mold them in the desired shape, and stability window is high. Now the question many people are asking, like why sodium electrolyte, sodium batteries, and so on. So the answer is they are having low cost and highly abundant. Electrochemical potential is good enough to realize a proper battery system, and potential of minus 2.7 volt with respect to standard hydrogen electrode. Apart from that, it has potential to giving energy density of 760 watt hour per kilogram. And you can obtain voltage greater than 2. If you need more, you can combine them in a series. Why sulfur? Sulfur is abundant, light, cheaper, and non-toxic. And the best part is the theoretical capacity is 1672 milliampere hour per gram, which is good enough for a battery system. And it has another advantage of 2 electron charge transfer reactions and good theoretical capacity. Sodium sulfur batteries, if we talk about, there are of 2 types: the high temperature sodium sulfur batteries, and other is the room temperature NS battery. Please remember that high temperature batteries are the conventional kind of NS batteries, and they are already commercialized. At the other hand, room temperature batteries is a developing technology and non-commercialized as on today. The high temperature sodium sulfur batteries, for such kind of batteries, the electrolyte is beta alumina and sulfur as well as sodium. They are in molten state because it is operating at very high temperature. So, and this is the example of sodium sulfur batteries, which is being installed at NJK Insulator Company of Japan. You can see this is the grid storage level at which these batteries are operating. But the high temperature operation of these batteries, this appears problematic, and that's why people are looking for the other alternates. The main drawbacks are these batteries are having substantially high temperature to be maintained, and beta alumina is poor conductor at room temperature, so obviously you have to operate at high temperature, and molten state is corrosive, reactive, so multiple problems. The research progress of sodium sulfur batteries indicates that for such kind of battery system, the interest has increased over a period of time, and people are exploring this system because of the specific advantage. If we talk about, then power consumption for maintaining the operation of the battery is negligible, and operating at room temperature has multiple choices. Molten state of sodium, as we mentioned, is corrosive, so operating at room temperature will be like addressing those issues. If we look at the principle and working of the room temperature NS batteries, then you can see from the sodium, the ions are traveling through the electrolyte and they are reaching to the electrode, and depending upon the product form, the sodium sulfide form, accordingly it will be having a different charge capacity. You can see from this diagram, if it is NAS, it is Na2S, it is having highest specific capacity of 1600 milliampere hour per gram. The electrolytes and the batteries generally face these kind of challenges. So the NS batteries are also facing these challenges. The challenges includes the interfacial contacts and capacity feeding, and many time thermal capacity, dendrite formation. So these problems are in lithium system also, and same problems are in sodium systems also, and one has to address these problems to fabricate better kind of energy storage systems. The timeline development, if we see that the research started on the room temperature sodium sulfur batteries from the year 2006, in which polymer electrolyte has been fabricated by Park et al, and they are having the conductivity of 10⁻⁻⁴ Simon centimeter inverse. And subsequently, the research efforts have been for developing various kind of electrolyte systems, including the solid electrolytes and other polymer cell electrolyte systems. The Zhao et al, they have fabricated a polymer gel electrolyte in which they have achieved a very good electrochemical performance. The electrolytes for NS batteries, if you look conventionally, you can use liquid electrolytes, then choices are carbonates, the TGDME, and some additives. The solid electrolytes, the choices includes Nasicon kind of systems or P2S5 kind of systems. The polymer gel electrolytes, you can have multiple combinations. If we look at the plus and minus of each systems, for the liquid electrolytes, conductivity is no doubt high. That's why even today they are preferred. But these systems are prone to leakage and short circuiting. So people are trying again for the different kind of systems. The solid electrolytes are having better safety, reliability, but again the interfacial context is a problem. For the polymer gel electrolytes, the conductivity is high, they are leak proof, good interfacial properties, but the results has shown that capacity retention is an issue. So now I am showing some recent studies which we have performed. This work is done by my PhD student. So in which we have prepared a cocktail kind of electrolyte system, utilizing the carbonate and tetraglyme and the ionic liquid in different ratios. This is how we have prepared the electrolyte system, and the whole cocktail system we have entrapped in a polymer matrix. The cassette plot shows that the bulk resistance of this electrolyte system is very low, which indicates the material is going to be good ionic conductor. And in fact, we have observed the conductivity of 10⁻³ Simon centimeter inverse, which is considered to be good for any electrochemical system. We have also plotted the AC conductivity features, and from that we can see at the low frequency the polarizing effects are prominent. At the same time, if we are moving to the higher frequencies, then the conductivity is being saturated and polarizing effects are subsided. At the different temperatures, we have also seen that the conductivity is following the similar kind of pattern. However, the conductivity has enhanced slightly. We have also measured conductivity as a function of temperature, and we can see that conductivity is following the Arrhenius behavior, which indicates the movement of ions via open behavior. And since no abrupt variations are shown, it means there is no phase transitions which are occurring. The ion transport number, to know the percentage of the total ions which are flowing through the system, we have utilized the DC polarization technique, and we have found that the ion conduction is 99% ionic. The cation transport number is also determined using the Vincent method, and we found the cation transport number to be 0.3 for one system and 0.2 for the other system, and both are the cocktail system in which concentration is different. So then we have checked the OCV of the battery assembled using the electrolyte system. The OCV was of 2 volts, and the discharge capacity was of 300 milliampere per gram. And what we observe is, after the discharge, the impedance is increasing, and that's why the capacity is fading. So for addressing this issue, we have fabricated one more system in which TGDME has been incorporated, and PMMA has been utilized. For such systems, what we have done is we are getting OCV somewhat higher, 2.2, approximate 2.25 volts, and the discharge capacity of almost 700 milliampere per gram, which subsequently decrease a bit. But however, after 10 cycles, the discharge capacity was 300 milliampere hour per gram. It is important to know that these battery systems, the NS battery system operating at room temperature, is not fully optimized even today, and research is open-ended. So now I conclude. So flexible electrolytes are preferable because of high conductivity, good transport number, and ease of device fabrication. Physical electrochemical characterization on the cocktail system and the TGDME system reveal that they are having good potential to be used in electrochemical devices. Investigation further suggests that RTNS batteries can be commercialized after further optimization. Optimization of not only the electrolyte, it is optimization of the electrodes also, and then the interfaces also. Way ahead, we look at development of non-flammable electrolytes and checking suitability by various physical electrochemical techniques. We also look for fabricating and characterizing sodium-ion metal sulfur batteries. And after proper optimization, we will look for suitable commercialization or patent. these are some of our publication in the year 2021. So we have got 2 publications in Journal of Molecular Liquids, Elsevier. It is having an impact factor of 6, and other publications also. Thank you very much. If any questions.
Thank you so much, Professor Deepak Kumar.
Thank you.
Thank you for your interesting talk. The session is open for questions. We can take 1 or 2 questions.
Yeah. Any questions? Anyone?
The audience, they're requested to post their queries. If they have any query, they can ask. The session is open for queries. Okay, thank you so much, Professor Deepak Kumar.
Thank you. Thank you.
Yeah. Now we will move on to the next talk, and we invite Dr. Uday P. Singh to make his presentation. The title of his talk is Thin Film Solar Cell Technologies, Current Status and Future Prospects.
Okay, thank you. Let me thank first the organizer for giving me an opportunity to present my work. So I will be basically talking on the okay, I think it's visible now.
Yes, sir.
So I will be talking about the thin film technologies and the photovoltaics. Basically, it's the current status and future prospects. In between, we'll also try to highlight some of our work also in this. So I am from Kalinga Institute of Industrial Technology, Deemed University, which is Institute of Eminence also from Bhubaneswar.
Dr. Uday P. Singh, sorry
Yes.
for interruption. Can you increase your volume? If it is like microphone's volume is low, can you increase the volume of the microphone?
Let me check. Now it is okay?
Yeah, it is good, sir. Thank you.
So in the photovoltaics, basically is among a wide variety of renewable energy projects. So photovoltaic is the most promising these days because it's a pollution free. The input energy is abundantly available everywhere, that is the sun. It's also operate like a few of the solar cells which can operate also in the diffuse light also. Only the big problem in photovoltaic system is the high price of the solar modules. But now with the large production, the module cost have come down. So whenever one looks for any alternative to silicon, they will try to have the comparable efficiency, and the cost reduction is important. So if you see the the solar cell technologies, there's a lot of materials, basically crystalline, which is still dominating. But crystalline also you can have a multicrystalline or the monocrystalline. Then the thin film, so amorphous silicon is now obsolete nearly. Then you have the cadmium telluride based solar cells or the copper indium gallium diselenide, and recently the castrite has come. And those who are in the organic and the perovskite has dominated now the research on this thin film solar cells. So our focus will be mostly on the copper indium gallium diselenide and the castrite, which is the copper zinc tin sulfide or the selenide. So why silicon is so successful? Because high module efficiency, one can get up to 20%, high stability and reliability is there, mature modular technology, no environmental concern, and wide material availability. That is the success of this. So when one is going to compete with this, so one has to have similar advantage. Only weak point of crystalline silicon is a indirect band gap semiconductor, which has low light absorption coefficient, and the cost has come down with, due to the large production from the Chinese market. So if one looks for thin film photovoltaics, so it has to compete with the established crystalline silicon to achieve comparable performance with the promise of substantially lower cost. And then high production capacity with reduced material consumption and energy input. Other is the energy payback time. Energy I have not listed here. Energy payback time for silicon is basically around 3 years. Like how much energy you are trying to consume during the production, and how many years you try to recover that. That is 3 years. For thin film, mostly it's around 1 year. So advantage for thin film is thin layers. Like if you see the crystalline silicon, it's maybe around 200 micron or 150 micron thick. So thin layer of around 1 micron is enable low material cost. One can have continuous large area manufacturing, because in silicon you have different wafers, then you have to integrate it. In this case, cell interconnects are produced monolithically. You can have flexible and lightweight module also. And these are aesthetically superior advantage for BIPV application, that is the building integrated applications. Roll-to-roll production is also possible. And also have now recently, like people are going to for a tandem application like silicon and the CIGS, or silicon with the perovskite. So a lot of work is going on the tandem applications also. So as I told earlier, like crystalline silicon, you can see the thickness is too much, but thin film, you can compare within 1 to 5 micron, you can prepare. So I will try to focus on the copper indium gallium diselenide, which has the lab scale efficiency has reached around 23.4, which is comparable to silicon. Module efficiency is between 13, regular production is 13 to 14%, sometimes goes to 16 or 17 also. But still the market share is still, it's 16 data, but like 20 also, it's around 2 to 3% only. Not much has changed. So if you see this thin film like CIGS, this 23.4 is the highest. And then I will be talking about the CJTS, which is gone around 12.6, not here in this, 12.6, this one. This one is 12.6 is for the CJTS, that is highest efficiency achieved. Okay, so all these thin film which are running cadmium telluride reached 22.1. These are all the lab efficiency. CIGS 23.4, copper zinc tin sulfide is 9.24, and copper zinc tin sulfur selenide is 12.6. So a lot of work has to be done this, but like because last 3 to I think more than 4 years, efficiency has not increased for this castrite materials. We'll skip this. So our focus will be CIGS. I will give some brief introduction on the CIGS. I will skip this. So if you can see this, one can deposit by different methods like sputtering, which has given around maximum 16.7% efficiency. Co-evaporation means you are trying to evaporate all the material simultaneously, which has given efficiency of around 23 point, which is the highest. Like if you go to the Japanese don't use, because in this, this is a P-type material, then you have to make a PN junction, you use the cadmium sulfide. But the Japanese don't use cadmium as a toxic, so they use cadmium-free materials. They have achieved with around 22%. On the polymer substrate, that is the flexible polyamide substrate, the highest efficiency achieved is around 20.4. So this gives the, like you can have different process and different materials you can use. This is one of the modules CIS thin film developed by Solar Frontiers recently, which has given around 19.2% efficiency. Also, people try to replace some of the sulfur by selenium, which is CIGS-SC. Just a moment, I will take. And then some of the people try to replace some of the copper by silver, which is give AgCIGSC. Okay, so the people are trying to try to replace some of the material with the others, and then try to see like how the efficiency can change. So if you see the history for CIGS, like it's crystalline silicon from 75, it's around 20, more than 20%. So not much has been changed. Only few point, like it's a 24.5, so 24.6 maybe, that may be the change. For CIGS, you can see like 3-stage process come 95, so it increased to around 20%. Now post-deposition treatment of alkali metal has given the efficiency more than 23%. So that is achieved in 2016, and after that, I think it's stagnant. So just a brief review on the material of copper indium diselenide. It started with the copper indium diselenide, and then people try to replace some of the indium by gallium to change the band gap. So one can vary the band gap. So if you see the application, you have solar power plants, power supply in aerospace, decentralized power supplies. So a lot of applications are there. So it's a zinc chalcopyrite material. It's a zinc blend structure, copper indium diselenide, and then you try to replace some of the indium by gallium. So this is pure 1 electron volt, and then you can go to 1.6. So for best efficiency is achieved for around 1.2 electron volt. Okay, it's the same thing. So you can vary band gap from 1.04 electron pure copper indium selenide to copper indium gallium selenide, that is 1.68. It's again a direct band gap semiconductor, high absorption coefficient. Minority carrier lifetime is also more. Electron diffusion length is few micron. So only like what problem comes, like if you see the phase diagram. So this is alpha phase is a pure copper indium diselenide phase. So the band is very, and this is very narrow. Like you have to maintain copper between 22 to 24% atomic percent. So if it goes above 24%, then you form copper selenide phase, which is very highly conducting. If you go below 22%, then you have certain delta or beta, this is the defect states present. So yeah, one has to maintain this. That is some of the problem people faces during the production, like reproducibility problem. But people have seen, like if you try to partial replacement of indium and gallium, it will slightly widen this, not much. And also the incorporation of sodium into the CIGS film slightly widen this your copper concentration. But you cannot go beyond 24.5. It becomes device will be get shorted. I already told you like this band gap variation is possible. So you can have, I will just skip this. And this absorption coefficient, you can see like if you want to absorb more than 90% of light, you need for crystalline silicon, which is indirect band gap, you need around more than 100 micron thick material. But for this copper indium gallium diselenide or cadmium telluride or CJTS, copper zinc tin sulfide, one micron is sufficient. But sometimes because when you try to deposit 1 micron, you always get certain pinholes. So the people try to maintain between 2 to 3 micron. So if you see the typical device structure for the copper indium gallium diselenide, you start with a substrate, which can be a glass substrate or the polyamide if you want to have a flexible. And then for back contact, one uses the molybdenum, which is the standard. And then you have the copper indium gallium diselenide, which is referred as the absorber layer. It's a p-type material. Then you have to make a PN junction. Then you have a cadmium sulfide, which is a thin layer of 50 nanometer. And then you have a transparent conducting oxide because the light is coming on this way. So it's basically a bilayer. We have certain intrinsic layer of zinc oxide, which try to avoid any shunting path. And then you have the zinc oxide, aluminum dope zinc oxide or the ITO, which is the transparent conducting oxide. If you have a slightly larger area, then to collect the current from all over, then you have certain grid form of the nickel and aluminum. So this is the basic structure for the copper indium gallium diselenide. Same structure is applicable for the copper zinc tin sulfide. So so back contact generally is made by the sputtering. Then you have the absorber. Then you have different methods. One can do by co-evaporation, then one can do by sputtering, and then you can salinize it. For non-vacuum, you can have used the nanoparticling and then print and then salinizes, electrodeposition and then salinization. So a lot of variation you can have. Similarly, if you go for the buffer layer, which is cadmium sulfide, most people use. Japanese don't use the cadmium, so they use zinc hydroxide or the indium hydroxide. So all this mostly deposited by the chemical bond deposition. And then finally, like when you have the resistive layer and the front contact is by this mostly commonly this sputtering. So I will just discuss co-evaporation. That is facility available in my lab also. Like you have the 4 sources. which was the thermal evaporation source for the copper, indium gallium selenide. So you can always change the flux also, like depending on how you want to track the profile of this. And then you have the substrate, and the substrate is heated around 500 to 550 degrees C. So this is the system we use. This is funded by the DST. So you can see like these are the four sources: copper, indium, gallium, and selenium. So you can use all simultaneously. So we are controlling the flux by the temperature only. So temperature for different materials, you use different temperature to control the flux. We don't have in situ measurement for the flux and the thickness. So it's basically hit and trial, like you try to first optimize copper for different temperature and time, okay, how much thickness you are getting. So if you so depending on this profile, like initially started with the in 1980s, it started with the like you deposit copper, indium, gallium simultaneously, okay, and selenium is always there. So this has a limited efficiency. But in Boeing company has given this process, which is bilayer or the Boeing process, in which what they have changed, like they have a low indium gallium initially and copper high, and after a certain time they try to increase the indium gallium and reduce the copper. So they have a slightly normal grading band gap. Selenium is always there. And 1991, NREL has given a 3-stage process, which has given the highest efficiency, which is basically the double grading. In the first stage, there is no copper. They deposit only the indium gallium, and then they reduce the indium gallium to 0 and then increase the copper. In second stage, only copper they deposit. In the third stage, again, they reduce the copper and then indium gallium. So it gives a double grading. So this has given the highest efficiency, and most of the people are following this. Other method is like sequential process. Sorry. Which is like selenization from the vapor. So you take the substrate, you deposit the moly, and then you sputter the copper, indium, and gallium. You get different alloys also, and then you selenize. So initially, when you selenize in hydrogen selenide, it gives the highest efficiency. But hydrogen selenide is very toxic in nature, so people try to avoid this because the university or the research lab generally it is not advisable unless you have certain precautionary. In India, like not much precaution is being taken. So it's not as advisable to take this, use this hydrogen selenide. So in that case, people have tried to deposit one selenium layer on top of that and then try to annihilate. So it's not very toxic, and then they try to achieve this. So in our lab, we have with this co-evaporation, we have got around highest efficiency around 11% on this small area, 0.5 centimeters square. So if you see the status, like this is like different methods. So there are different companies which are doing co-evaporation on the glass using sputtering method, electrodeposition, or the printing. And if you see the substrate wise, so glass, this much companies are doing now. They have a lot of company have stopped or they merged. And then flexible substrates, people are using on the stainless steel. Some people are using copper, aluminum, and the plastic. So now most people are surviving on the plastic, which is the polyamide, like Filmson, this A.N. Tiwari group in Switzerland, then Essence Solar in Germany. I will skip this sodium concept. So for the flexible is the polyamide moly process is the same. Only thing you cannot go above 400 because this polyamide substrate is maximum temperature it can take around 450. So you have to deposit CIGS more less than 500 degrees C. Rest process is same. So this is the standard process now people are using. You have a glass or metal plastic foil, then you to coat the moly as a back contact, then you have the copper, indium, gallium selenide. During the process, you form some of the moly sulfide or selenide. Then you have some post-deposition treatment of the alkali metal like potassium. Mostly people are using potassium. Then you do the cadmium sulfide, and then the zinc oxide, which is your intrinsic zinc oxide. Then you on top you have the highly doped zinc oxide. So that is the structure people are using. So recently, if you see, like, these companies are surviving for on the polyamide essence solar, Flisam, stainless steel, Mia Solar in US, Solar Power, and then Global Solar Energy and Han Energy is this Chinese company which has acquired this Global Solar, and Solar Frontier on the glass. So in our lab, like during this pandemic, like we are not able to do any experimental work, so we have moved into some theoretical work. So we have proposed a bilayer CIGS device for enhanced performance. I will just give a few glimpses on that. We cannot go into detail because time is limited. So what we have proposed is Molly. Then you have a CIGS layer, which has around 1.28. So total thickness of CIGS we want around 2 micron. So we have divided this. We have optimized this. So on the top layer, 1.15 electron volt with thickness around 0.4 micron, and this is 1.6 micron. So there is a, like, if you don't use any interfacial layer, there is a possibility during high temperature process, there is a problem like some interdiffusion will take place, and then you cannot maintain this stoichiometry. So what we have proposed for first time, like if you use moly sulfide, so we have optimized for different thickness. So 30 micron, 30 nanometer has given the best efficiency. So this will give a gallium grading also, and this is done into the simulated work. So different parameter has to be optimized. Okay, so this has given us best efficiency around 24.17. So we have also compared with the different results also, like some experiment single absorber layer which has given 23.35, which is the highest. There are certain simulated result also present, like bi-layer and then the single layer which has given 22.20 or 23. Recently, in 2018, single layer experimental which has given around 23%. So this is our present work which has given around 24.17, which is recently published in Applied Physics. Some of the applications. Now, because there is certain problem in the copper indium, if you go for gigawatt or terawatt, then the scarcity of indium is there. So people try to replace some of the indium and the gallium. So people have come with the copper zinc tin sulfide or the copper zinc tin selenide. It's again high absorption coefficient material, p-type semiconductor. Zinc, which is 20,000 times more abundant than indium. Tin is also abundant. So these are earth abundant and non-toxic materials. Only thing is limited is now deep knowledge on material properties still not there, because people have started and then people are only trying to focus on the getting the efficiency. So material property is still not well studied. So deep knowledge on material property is still limited. Process better suited for casterites, better contact materials. Like if you see the funding agency, like in India, like DST is the major funding, and also you have the Ministry of Non-Renewable Energy. They always ask for some result, like oriented, like what efficiency you will give. For basic research, like funding is limited. So this material properties is still limited. So if you see the structure, it's the same, moly, then you CJTS, and then finally you have the CDS and this. So highest efficiency achieved is only 12.6, that is only on the lab scale. So this is for the tin sulfide. You can see like people have used different methods, and solution based has given 9.24 efficiency, that is also in 2015. So no increase in the efficiency for 6 years in this material, copper zinc tin. Similarly, if you go for the copper zinc tin selenide, it has given, using co-evaporation, it has given 11.6%. That is again 2014. Again 7 years, no increase in efficiency. And similarly for sulfoselenide, the highest efficiency is around 12.6, which is hydrogen based material. And then sputtering people have to do. So it's again 2014. So again 7 years, no increase in efficiency is observed. Material property is same as the CIGS. Structure, I told you, like device structure is same. CJTS, CDS, IZNO, and AGM. So in our lab also we have tried to deposit by trying to make this copper zinc tin selenide fabrication. So we have used copper tin, then zinc, then selenium, and then zinc, then copper tin. So this we have got by different optimizing different layers. So thickness is around 1.32 micron, and then they were salinized with the selenium at different temperature. We have used two-step annealing, 230 degrees C for 10 minutes, and the second step we have gone around 450 degrees C. So this is XRD. We get basically all the CJTS peak. No other binary phases are available present there. So highest efficiency what we achieved is only 3.97%. This is on the small scale, which we published in the superlattice microstructure in 20. So still a lot of work has to be done in this material. There are certain limitations like short magnetic area lifetime, high concentration bird defects, grain boundary characteristics. So one has to like, people have now tried to introduce germanium as the obvious candidate which can increase the VOC. A lot of work is being done on this, but still the efficiency is not moved beyond that what we have shown earlier. In this case also, like in this pandemic, we have also done some theoretical work. It's a normal grading. Okay, so we have again used CJT as 1.5 electron volt and CJT SC here is 0.9 electron volt. And then we have introduced MOS2 just to avoid the interdiffusion so that the band gap should not change. So you have a grading of the band gap. So light is coming from this side, 1.5. You know, AG is around 3.3 electron volt, CDS 2.4. So most of the light will reach to this. So in this case, we have used WXMPS software. So highest efficiency, what we achieved, this theoretical work is around 21.06. So this has been recently published in Solar Energy. So CJTS is new emerging technology, maybe a long way to go. Like people have to concentrate on the material properties. So like working on thin film, I can say like thin films have the greatest potential for low cost production and will dominate the future of photovoltaics. That's all from my side. I'd like to thank my teammates in the lab and the financial support from MNRE and DSP SCRB for this. Thank you. If you have any question, any query, I will be happy to answer this.
Okay, thank you, sir. Very nice presentation and about the thin film solar cell technology. Any query from participant side? There is no query in chat box also. So, sir, thank you for your informative talk. And you have described all dimensions of thin film solar cell. Because of no query, I would like to call next speaker.
Okay, then, thank you.
Okay, sir, thank you. Next speaker is Dr. Sabrina Corolla from Italy. Hello. Hello, ma'am. Hello. Hello, Dr. Venus.
Yes, sir. We are waiting for her response, sir.
Okay.
We are making announcement once again. Dr. Sabrina Carola Caroscio. Are you there in the presentation? Are you there in the audience? Dr. Sabrina, you are requested to make your presentation.
I think yes, is not.
Dr. Sabrina from Italy. Her talk was on polymeric hybrid cryogel for water remediation. Sir, I think we should proceed further and invite the plenary talk, sir. We should invite the plenary speaker, sir.
Okay.
Yeah. So please introduce the plenary speaker.
Okay.
Yes,
next, yes. Next topic is from Professor Shailen Jaffer from Turkey. This is the plenary talk, and I would like to brief about the Shailen Jaffer. Shailen Jaffer is a professor in Department of Energy Technologies in Solar Energy Institute, Egg University, Turkey. His research interests lie in the area of solution processable organic hybrid materials for
optoelectronic devices. These semiconductor materials poses a valuable platform for printed, large area, flexible, and variable electronics that can be used as a solar cell, smart windows, OLEDs, OFETs, sensors, and bioelectronics photocatalysts. Professor Jeffer is particularly interested in interface engineering for organic hybrid solar cells, perovskite solar cells, dye-sensitized solar cells, transparent solar cells for building integrated photovoltaics and stability degradation studies for long lifetime perovskite and organic solar cells. Professor Zafar has led projects on donor acceptor low band gap conjugated polymers for organic solar cells. Second one, non-fluorine acceptors for ETL for perovskite solar cells. Third project has upscaling and module fabrication of perovskite solar cells. Next project he have in his credit quantum dot conjugate polymer composite for optoelectronic devices. He spent nearly 20 years on the synthesis, characterization, and utilization of organic and organometallic semiconductors for solar energy harvesting and optoelectronic applications. Professor Zafar has co-authored about 60 SCI papers, and he has 3 European patents in his credit and more than 100 conference proceedings related to next generation photovoltaics. So I would like to invite Professor Zafar for his presentation. Okay, Professor Zafar, over to you, sir.
Yeah, okay. Thank you, Chairman. Thank you for a nice introduction. Am I audible?
Yes, sir. Yes, sir. Audible.
Okay, okay. And first, I would like to thank for a very nice organization and for the invitation for this conference. I'm going to share my screen. Is it visible? Okay.
Yes,
okay. Hello again. I'm Ceylan Zafer from Turkey, from Ege University. I'm a member of Solar Energy Institute. Ege University is located in the west, most western part of Turkey. It's a seaside city. It's a beautiful city, and Ege University is the third largest university established in Turkey. Yes, Solar Energy Institute is only one institute in Turkey dedicated to research on renewable energy resources and technologies, especially in solar energy. Yeah, the institute is well equipped with a large number of facilities, especially on the material science for the renewable energy technologies, with the mostly for the organic solar cells, hybrid solar cells, and the development of the energy related materials, with the clean rooms, with the large number of glow boxes to work under ambient conditions and inert conditions. And especially recently we moved to make a research on the upscaling of these solar energy technologies by using different kind of coding techniques. Yes, After brief introduction of the city and the university, I would like to show my outlook of talk. I will talk about the new approach to enhance the stability and the performance of perovskite solar cells, especially on the triple cation perovskite solar cells. Yes, we know all there's a very huge source of energy coming from the sun to the earth, and we don't need a different kind of energy sources like an oil and gas. But you know, the earth is very small in this huge amount of energy, and we can use and utilize this energy easily by using different kind of technologies. The most familiar one is photovoltaic. And if you look to the energy spectrum of the sun, of the energy resource coming from the sun, with this blue spectrum, and we have to separate these energy spectrum into the parts to utilize efficiently. And for this one, we use a different kind of technologies for the photovoltaics, and you can easily see the chart is published by NRER. It's very well-known chart, and it combines different kind of photovoltaic technologies with the best solar cell efficiencies, certified solar cell efficiencies. And I'm talking with the photovoltaics located here. It's a perovskite solar cells called perovskite solar cells, and here you will see another one. It's a kind of hybrid silicon perovskite tandem solar cells, and it's almost reached the 30% efficiency. And here you see the module efficiencies, and the previous slide was the cell efficiency, and this is a module efficiency. And because the perovskites become a commercial product, and you will see this technology in the market soon. And here you see the perovskite from the First Solar, and the Panasonic will come here, and nearly the 18% module efficiency is quite competitive with the other technologies like thin film technologies and silicons. But the best way to use these perovskite solar cells integrated with the silicon or other thin film technologies to make a combination to increase the harvesting of the energy coming from the sun efficiently. If I'm gonna talk about the perovskite semiconductor, what's it? It's a kind of three-dimensional organic and organic hybrid crystal containing a metal center, and is surrounded by the halogens and the organic cations like a methylammonium or formamidinium, and that's why we call this crystal is a hybrid or organic inorganic hybrid perovskite material. It's an interesting crystal that can be modified by changing the stoichiometry of the composition, like by changing the stoichiometry of the halogen. And if you change the stoichiometry of the halogen and add another one instead of the iodine, it can be replaced with the bromine, and the band gap is changing very precisely, and we can harvest more energy by optimizing this ratio. On the other hand, we can play with the centered metal by except changing the stoichiometry of the halogen. Here you see by changing the cation also, it's changed the band gap, an optical band gap, starting from the methylammonium lead bromide from the 2.3 electron volts band gap. It's becoming by changing, replacing the bromine with the iodide. It's comes to the 1.5. by changing the cation again, we can slightly play with the energy band alignments, or by changing the center metal, by increasing the content of the tin together with the lead by 25% to 50% and 75%, changing and narrowing the band gap drastically. And that's why the perovskite become very popular in the solar energy conversion area. If I'm gonna talk about the geometry of the solar cells, there's different kind of and different geometries, but mainly two geometries are accepted for the research cells with the NIP geometry and the PIN geometry. There's a slightly difference between the electron and hole transporting materials and its inverted structure. And this depends on the production facilities. If you'd like to make a production with at the low temperatures, usually the PIN geometry is acceptable, because by using this geometry, you don't need to go to the high temperatures like 400, 450 to make a sintering of the metal oxide layer, because there is no metal oxide layer in the structure. And you can use this geometry on the plastic or flexible surfaces and also flexible substrates like a PET or PN. The real perovskite solar cell report came at 2012 by the group of Michael Gretz and Namil Park from Korea and the EPFL from Switzerland, and reported nearly 10% with the real perovskite solar cell device. And this paper was followed by the paper coming from the Henry Snaith from the Oxford group. And these two papers show that the perovskite is a really good absorber, semiconductor, can make a transport of hole and electron at the same time. This means that ambipolar material can be used in solar cells and efficient solar cells. But of course, the material need to be optimized, to need to be controlled crystallization, because this is a crystalline material and crystallization takes part, really important part in this process. And this is a solution processed material, and that's why the solvent is a crucial point of for the processing and for the fabrication of the device. And the first papers came with the dimethyl formaldehyde solution, and then with the gamma butyrolactone, and DMSO is also commonly used solvent for the production of this material. But the polarity of the solvent is very important to control the crystallization dynamics and for the morphology of the material. For example, if you work with the DMF, we obtain needle-like crystals. With the gamma butyrolactone, we obtain very small spheres of perovskite. And with the DMSO, we obtain large spheres of the perovskite. And with these three solvents, it's not so easy to get a proper morphology and crystal to get an efficient device. Also, the post-production treatments are so important to get a really aimed crystal structure. For example, the post-washing, or let's say we say washing of the crystal just after the casting on the substrate change the morphology drastically. And if you've seen, by washing of the toluene or another aromatic solvent makes a big difference in the crystallization, with the crystallization dynamics, and the temperature is so effective. Just after casting of the perovskite material and washing with the toluene improves the crystal quality, And here you see that's just one drop of the toluene makes a big difference in the structure of the crystallinity on the perovskites. This means you will have a better structure for the transport of the charges within the absorber. This is also checked with the absorption and let's say electronic spectra, and this makes a small difference in the optical properties of the perovskite. And here you see this enhances the molar absorption coefficient and also small difference in the absorption edge of the material. And this can be easily seen in the photoluminescence spectra. There is a difference between the washed and non-washed materials. If you look to the charge dynamics and the photophysics, what's going on deep in this material, comparing to the washing and non-washing films, we will see the dynamics are also changed in the material. With the washing of the material, it's become slower of the decay of the charge, excited charges. And this means we will have a less or slow recombination in the material. And with the photoelectron spectroscopy, we observe that there is a difference in the band gap between the washed material and the non-washed materials, which is very important for the device performance. With the washed materials, the band gap of the materials is around 530. With the non-washed one is a 52. This makes a better alignment of the energy levels for the whole transport within the material between the P-type spiral material and the perovskite material. And this can be easily seen on the performance of the device in the IV curve. And then nearly 5 years later, after publication of the first paper of the perovskite solar cells from the group of the great cells, that came a very important paper giving us information about the triple cation perovskite, because the perovskite is a very interesting material. With only one cation, it doesn't make a so stable crystal, and the crystal should be stabilized with additional cations. And there is a different phases which are non-photoactive for the perovskite solar cells. And insertion of the cesium and formamidinium to the methylammonium lead iodide perovskite improves drastically the performance and the crystal quality of the perovskite. And as seen from here is the work performed in our laboratories. The cesium, formamidinium, methylammonium, lead, iodide, bromide. This is a triple cation and double anion perovskite. We got a really good efficiency and really good, very nice performance with the perovskite solar cells. And is this enough for the performance improvement? No, because there's still, let's say, some problems should be resolved within the structure. For example, the alignment of the HOMO level of the perovskite with the whole transporting material spiral is not so perfect, yeah? And we made the doping of the spiral method for the better alignment of the energy levels. And for the doping of the spiral method, different P-type dopants like cobalt and antimony salts can be used. And for this one, if you see from this energy band diagram, better alignment of the perovskite and between the spiral method can be seen upon doping of the spirometers, and the relative conductivity of the spirometers increased drastically upon doping with the FK 209. And what's the effect on the device performance of this? And the efficiencies improved nearly 19. Yeah. Another performance improvement strategy for the perovskite solar cells known in the literature is titanium oxide, which is an N-type transport layer within the device, should be doped with like a lithium ions, which removes the defects of the titanium oxide located between the Fermi energy level of the titanium oxide and the conduction band. And these defects make a non-radiative recombination centers and increase the recombination ratio of the device. By doping of the lithium within the titanium oxide, improves the device efficiency as seen here. And now we got an optimized N-type material, P-type material, and perovskite material for the improved efficiency device, so perovskite devices. And these are known in the literature, yeah. And recently we checked that with the impedance spectroscopy. Is it really so effective in the device performance and the charge carrier transport? And you see the recombination resistance is so high compared to the non-lithium doped material. And this means that recombination ratio is very low compared to the earlier one. And the transport is unchanged. In my talk, the new information is coming with the new approach to enhance the device performance by playing with the solvents. In the literature, the conventional method is just replacing the solvents with the different polarities. But in our studies, we use reactive solvents that reacts in the in situ with the perovskite material and changes the morphology. And one of them is the chlorobenzene. It is by using the different solvents instead of the chlorobenzene, like a benzyl bromide or benzyl iodide. Here you see this is a normal energy alignment of the perovskite device with the two interfaces with the lithium treated titanium oxide and the spirometer interface. For this one, we play with the perovskites itself, the crystal structure, and these two interfaces. With the first one, we used benzyl chloride and benzyl bromide instead of chlorobenzene, and with this changing of the solvents, we observed some differences within the perovskite crystal structure examined with the X-ray diffraction studies. And this peak located at the 12.6 is a common peak of the perovskite material coming from the lead iodide. And the peak intensity will show you the crystallinity structure is located, and small shift here you see with the 12.6 to theta degree, there is a small shift. This is an evidence of the insertion of the larger ionic radius halogen into the perovskite structure. Here you see the morphology changes with this treatment of different solvents. Here the particle becomes a little bit larger with the chlorobenzene, with the benzyl bromide. It becomes again with the smoother, with the RMS roughness here as seen. With this benzyl bromide or benzyl halogen treatment, the reactions goes through the Korn-Bloom oxidation reactions, and the key point of this reaction is the removal of the very strong coordinating solvents that we use for the preparation of perovskite solar cells. And in the literature, it's very well known for the perovskites, the DMF, DMSO with the ratio 1:4 is the best configuration for the preparation of the efficient solar cells. But the disadvantage of this mixture with the DMSO and DMF are very strong coordinating solvents, making a coordination with the metals like a lead or tin. And these coordination products, or let's say byproducts, are acts like a traps or non-radiative recombination centers, which inhibits the charge transport within the structure, within the device or within the perovskite structure. And here, as seen here, with the within the production process, with this reaction between the benzyl bromide and the DMSO, we get rid of the DMSO by changing to the benzaldehyde and dimethyl sulfides. The benzaldehyde and dimethyl sulfides easily evaporable at 100 degrees by annealing, and we can get rid of these complexes from the structure. This can be examined with this electronic spectra, yeah? And here seen this is a absorption of the perovskite, and these are absorption of the lead iodide washed with the chlorobenzene, benzyl chloride and benzyl bromide. And here you see the fluorescence spectra of the perovskite. And it's a lasing behavior. This shows a very nice crystal structure. And we examined with the transport and lifetimes of the perovskite with the excitation nearly at 405 nanometers, and you see the slow recombination of the perovskite material washed with benzyl bromide, with the green one, with the black one is a chlorobenzene reference control material, and with the fast recombination with the benzyl chloride. For the, let's say, with the exciton, or let's say exciton recombination takes part in longer time with the benzyl bromide, but with the independent free charge carrier recombination is faster with the benzyl bromide. This means that with the fast transport with benzyl bromide is it's an advantage within the device to get a best efficiency. This is proven with the XPS measurements. What's the source of these results? And we see that the interaction of the bromine anion here is seen very well with the DMSO, with the benzyl bromide that takes part in the this process by interaction of the bromine and sulfide, which is coming from the DMSO. What's the result on the photovoltaic performance? Here you see with the benzyl chlorobenzene or benzyl bromide, let's say the black one is the chlorobenzene. With the device efficiency here, these are forward scannings with the 18.6% efficiency, with the benzyl bromides 19.2. These are forward sweeps. That's the reverse sweeps makes a big difference compared to the benzyl with the perovskites. when you make a forward scan, because there is a small hysteresis between the forward and backward scan in the perovskite solar cells. Here you see the data summarized for the device efficiencies. These are the average photovoltaic parameters for the best cell with the benzyl bromide and the chlorobenzene control device. And here you see the forward and reverse scan for the materials. And the hysteresis becomes smaller with the benzyl bromide washed solvents. The benzyl bromide produces an hydrogen bromide, and this hydrogen bromide dissociates the bromine ion and the hydrogen, and the bromine it makes an insertion within the perovskite structure, and this is seen very well within the X-ray diffraction pattern. And with the impedance spectroscopy analysis, again for the benzyl bromide washed perovskite soil cell, the number of the densities are smaller compared to the others. This makes it less number of the defects within the crystal structure can be obtained. Another similar work with the perovskite material is using then acetamide, like bromoacetamide and iodoacetamide and chloroacetamide solvents, again with the perovskite structure. This is quite similar to benzyl bromide because the byproduct is a hydrogen iodide and reaction of the acetamide with the lead iodide and produces the hydrogen iodide, or let's say hydrogen halogener, which is then reactive with the perovskite structure itself. And we got really again enhancement in the efficiency of perovskite solar cell and also in stability. Again, we check with the crystal structure, with the XRD and with the main perovskite peaks located at 12.6, and again with the 34 here, with the electronic absorption spectroscopy here. We check again the photoluminescence and the lifetimes of the photoluminescence spectra again, and we got a similar results with bromoacetamide, like a benzyl bromide compared with the previous work. And this is really interesting because the both solvents produce the hydrogen bromide, and the hydrogen bromide interacts with the lead iodide perovskite. And we check this reaction under NMR conditions and what's going on with the NMR and in the molecular manner. And here we observe that's a conversion of the bromoacetamide, and it makes a reaction with the lead ion here over the oxygen. And this is correlated again with the XPS, what's going on. And oxygen intensity makes a difference here, like a bromine atom analysis. And if we come to the device performance output here, you will see that again with the benzyl bromide, we got an better efficiencies and better performance, better stabilities with the IPCE again, and here you see the IV curve of the device, and the data is summarized again here. Again, we check with the what's going on with the impedance spectroscopy for the charge transport, and with the benzyl bromide here you see the transport time is shorter. This means faster transport within the structure, and the recombination time is longer. This means a slow recombination takes place within the perovskite structure. This comes with the recombination resistance with the material, with the benzobromide compared to the others. It's a very huge recombination resistance. And that's why going beyond the conventional structures and conventional processes, yeah, the perovskite solar cells giving a promising aim for the future, yeah. And that's why nowadays several companies start to release their commercial products like an Oxford PV from United Kingdom. The factory is located in the Germany. From China, the CGL, another one. From Soliance Consortium coming from the Netherlands and the Belgium are some companies that are releasing their commercial large area products here. Here you see the tandem solar cell of the Oxford PV, and this is fabricated on the crystal, silicon crystal and top perovskite solar cell. Here are my conclusions that we obtained from the our works, and we see that the reactive solvent treatment and the reactive solvent process to enhance the stability and the device performance are effective to get a really good performance perovskite solar cells. I would like to thank for my team, my faculty members, Burak, Halide, and postdocs, Denis, which worked hard in this works. The PhD students, Adem and Tamer, also have worked hard on these works. And I would like to take my students to my collaborators, Canan from the İzmir Technology Institute, had a talk the first day. And especially to you for your attention, and to the Sharda University organizing this nice conference and invitation. Thank you. I can take questions if you have.
Okay, thank you. Thank you. Thank you, Professor Jaffer. Now, this presentation is open for query. If from participants, if you have query, then you can ask your question. Current. Okay, I think yeah, there is no query in chat box. So, Professor Jaffer, I have a question.
Yeah.
Very simple question. Will it possible to prepare the perovskite solar cell in open atmosphere? Can we remove the glove box for preparing solar cell?
Sorry, your voice is not so hearable. Can you repeat again, please?
My question is, will it possible to prepare perovskite solar cell in open atmosphere?
Actually,
can we
yes.
remove the glove box for preparing solar cell?
Actually, all work in our laboratory is prepared in glow box. Yeah, take part in glow box, but with the triple cation perovskites, you can work also in the ambient conditions without the glow box. Actually, the Izmir is a seaside city, and the relative humidity of the air is so high, above 70 and 80%, and that's why the moisture in the air is so destructive for the perovskite structure. It's the polarity and the dipole moment of water is so high, and you know the perovskite is really very weak crystal. Yeah, comes together with a very small and let's say small forces. Yeah, and with the solvents with the high dipole moments can break the crystal, and the water is most hazardous material or the chemical that breaks this crystal. if you work with the relative humidity below 40%, you can easily work in under ambient conditions, especially with the triple cation perovskite. As I mentioned in my talk, that the only one cation methylammonium perovskite has several phases, like a yellow phase and a black phase, which are inactive or very sensitive to the air. To going to the double cation, like a formamidine and methylammonium perovskites, makes it a little bit stable and efficient, but still some additional phases takes place in the product, and these additional phases reacts like a recombination centers, and that's why cesium, like with a ion with a very large radius, putting into the crystal makes a really good stabilization. Yeah, and that's why with the triple cation perovskite solar cells you can easily work in under ambient conditions.
Okay, okay. Thank you, sir. One another question that is asked from Professor Bhattacharya. What is the stability of these cells in open atmosphere? This is similar one.
What is the
stability of these cells in
stability? Okay, okay, okay. I didn't put the data of the stability, but the stability with the device that we start to measure in our devices in our in the laboratory conditions about 8 months. We have a device that survives during the 8 months, and we check time by time the stabilities, and the efficiency is 85% of the initial efficiency. And we, at the same time, we do the accelerated lifetime cycles within the solar climatic chamber.
Okay. So,
and of course, within the climatic chamber, they degrades fast because there is a factor of the acceleration, something like that. But under ambient conditions, nearly it's around 8 months, we have a device still survive.
Dr. Venus.
Another questions?
Yes, sir. There is one more question from Dr. Biono.
One more
Did you perform? Shall I read the question, sir? Did you perform cost analysis feasibility studies?
Actually, we have just made we have just started to make a feasibility analysis here for the, let's say, governmental organization that asked for to make a feasibility analysis of the perovskite solar cell production, especially in Turkey. We compared with the United States and Europe, and for the perovskites, it's around now for the 100 megawatt per year production capacity. It's around 0.57 cents per watt, the price. But this depends on the production capacity. If you go to the 1 gigawatt, this goes down. If you go to the smaller capacity, it goes up. For the 100 megawatts, it's around 0.57 cents per watt. Okay. At the moment, for the beginning, if you compare with the silicon, it's a little bit higher, yeah. But this is a new emerging technology, and the costs are a little bit higher now.
Yeah, Pandey. SP.
Okay.
SP Pandey.
Thank you, sir.
Sorry, Pramod, do you have any question?
No. I do not have any question. I am just appearing from my friend's laptop. So nobody knows that Pramod is in front of you. Most people knows that at least Dr. Sunil is in front of you, but you know that Pramod is in front of you.
Okay.
And I think now question hour and everything is finished. I think this one is a nice chance to introduce all of my my colleagues in front of you. Basically, you can see in front of your screen, there is one very senior, you can say, our moderator or our motivator for this solar cell area is Professor Bhaskar Bhattacharya. Now he is in front of your screen.
My best
And-
regards, and I'm really proud. Yeah, I'm really proud.
Another
My
one,
best
my
regards.
friend is, I think, who is chairing the session chair of this conference, Dr. S.P. Pandey. Dr. S.P. Pandey and myself, we got degree in same date with same institute.
Oh, nice, nice. My best
And,
regards, and thank
yeah,
you for
yeah.
the chair. Yeah, thank you for the organization and invitation. Thank you.
And
Yes,
I
I'm
think
glad
in
also.
front of you, my colleagues, Dr. Venus already, she's very nice, kind lady. So they, I know the Izmir atmosphere point of view. I think they want to visit at least one time in Turkey.
Always welcome, always welcome. Yet, and we are open for collaboration. We are always welcome for the visiting. Yeah, and for that's same for us. Yes, and let's start a trip and for the let's say bilateral and two-side trip.
Yes,
And
yes.
always welcome for the visiting. Yeah.
Yeah, so I think now another one professor, maybe Dr. Maria is in front of. I saw this lady, nice face every time. So I am thankful, Maria. At least you can join from, starting from, you can say Indian time till last time. It's very rare for us. So I think since there is no nice introduction, you can say introductor point of view, I think I have one person who have close relation with Professor Jilan. He already know. I work with him in 10 months, not directly, maybe indirectly, he knows better than me. I came here as a to be Tech Fellow to work in his own institute. Now he is presently director of that Solar Energy Institute, very big position. And although he has very, you can say, busy schedule and every appointment, so I am always thankful to Jelan to giving me time at least. So Jelan, I'm very thankful to you, and I think in front of you, we are trying to perform this conference in 100% online mode. It is just trial version from our own side. So if there is lacuna, please forgive us. Okay, and I think in coming time, I will always like to see your happy face in front of us and your group too. Thank you, Jelan.
It was a big pleasure for me, and after these pandemic conditions,
yes,
I'm looking forward to come together in the real face-to-face conference. Yeah, and my best wishes also to India for the let's say to escape easily and fast from these pandemic conditions. Yeah. Okay.
Thank you. Thank you. Now its mic is over to Dr. Venus Dillu.
Thank you so much, sir. And I would like to thank Professor Zelan Zafar for such an interesting talk. And thank you, Professor Pandey, for hosting this session. Thank you so much for chairing this session, sir.
Thank you, ma'am, also.
Yeah. So we are closing the
I
session.
am very much thankful to Professor Pramod Singh, Professor Singh, and all team members of Sardar University. Professor R.C. Singh, Professor Pramod Singh, and other professors like Dr. Mohit, you, and everything. I'm very much thankful to all of you giving me opportunity to chair the session for a nice, interesting conference. Thank you, ma'am. Thank you.
Our pleasure, sir, and thanks for sparing your time, sir.
I think
Now,
Bhaskar sir want to say something.
Bhaskar sir, your voice is not coming. We are giving you right.
Yeah, I gave the muted. Hello, Professor Zafar. It's nice to see you and nice to hear you. It was a really excellent talk. We would definitely like to have you physically in India sometime.
Yes.
Once this pandemic condition goes up, definitely we would like to invite you, and so that you can come here, we can discuss and talk to you.
Okay, thank you, sir. Thank you. Of course, yes, I'm looking forward to see you physically.
And we are also going to provide Indian nice curry because he loved with Indian curry, I know.
Oh, that's great.
Okay, Venus.
Thank
Now
you.
it's my
Thank you,
turn.
Dr. Venus.
Okay, thank you, sir. Dear participants, there are 2 parallel sessions running, which will end at 1:30. So if you are interested in any of the talks in session 3B or 3C, you can join the session. This session is closed for lunch, and we will be meeting again at 2 p.m.
No, I think that other 2 sessions have already closed, just 5 minutes before. So we are just waiting for next session, means starting from 2 to 5 p.m.
Okay,
It's
so
oral
next
session.
Yeah, we will again meet at 2 p.m. The sessions are closed for now, and there'll be again 3 parallel sessions. 3A will be 3D, and 3B will be 3E, and 3C will be 3F.
And Venus, I think there are 2 judges for this oral session.
Yeah, for this oral session, the judges are Dr. G.N. Pandey and Dr. Denise will be the judge of this session for the oral talks. Yeah. Sir, I think we will introduce them later at 2 o'clock.
Yeah. I think just I want to announce only one thing, that in both, you can say 3 parallel oral session, third D, as Dr. Venus already told, the judges are Dr. G.N. Pandey from India and Dr. Deniz from Turkey. I think Dr. Deniz is a student of Professor Jelan. He already in front of me. And in next one session, means third E, the judges are Dr. K.K. Pandey from India and Dr. Alexandra from France. For third, I think third F session, the judges are Dr. Meenal from India and Dr. Maria, she is already in front of us, from Italy. So these are our 3 parallel oral session. I invite all of you to join after lunch, means Indian time started from 2 to 5 p.m. Thank you everybody.
Thank you, sir.